All right, great. So I can introduce you all. One quick announcement before we get started.
Sure.
It is the first week of class, so I need to leave to go teach at around 9:45 Pacific time. Sai and Ghosh should be stepping in around 10. There might be about 15 minutes without a moderator here, just so you're aware.
Yeah, sure.
Okay, great. So we can get started. This is going to be the tutorial for high performance machine learning, deep learning, and data science principles and practice. The speakers are Dhabaleswar, Panda, Subramoni, Aamir, Shafi, and Nawras, Alnaasan. A little bit about our speakers. So Dhabaleswar Panda is a professor of computer science and engineering and a university distinguished scholar at the Ohio State University. He has published over 500 papers in major journals and international conferences. Dr. Panda and his research group members have been doing extensive research on modern networking technologies. Dr. Panda and his team have been actively working on high-performance MPI and PGAS libraries, deep learning libraries, and big data libraries. Dr. Panda is an IEEE fellow and a member of ACM. Dr. Subramoni is an assistant professor in the Department of Computer Science and Engineering at the Ohio State University. He has published over 100 papers in international journals and conferences. He has been actively involved in various professional activities in academic journals and conferences. Dr. Subramoni is doing research on the design and development of MVAPICH 2 and MVAPICH 2X software packages, and he is a member of IEEE and ACM. Dr. Aamir Shafi is a research scientist in the Department of Computer Science and Engineering at The Ohio State University, where he is involved in high-performance big data project led by Dr. Panda. Dr. Shafi was a Fulbright visiting scholar at MIT in the 2010-2011 academic year, where he worked with Professor Charles Liserson on the award-winning Silk technology. Dr. Shafi received his PhD in computer science from the University of Portsmouth in the UK in 2006. And Dr. Shafi co-designed and co-developed a Java-based MPI-like library called MPJ Express. And then finally, Nawras Alnaasan is a graduate research associate at the Network-Based Computing Laboratory in Columbus, Ohio. He's currently pursuing a PhD in computer science and engineering at The Ohio State University. His research interests lie at the intersection of deep learning and high-performance computing. He works on advanced parallelization techniques to accelerate the training of deep neural networks and exploit underutilized HPC resources. And he received his bachelor's degree in computer science and engineering from The Ohio State University. So thank you very much, and we look forward to your tutorial.
Yes, thanks a lot, Amanda, for introducing all of us. Good morning, all of you. It is a pleasure to present this tutorial today. Before we get started, might be just few of you, if you can just introduce yourself, just tell us a little bit about your background and why you are interested in this tutorial. That will help us a little bit. Any volunteer?
Hi, I'm Teresa Schofield. I'm a 35-year IEEE member in the UK. Started my career as a chip designer at Texas Instruments, worked when Wally Rines was in charge of micros in Houston. I was privileged to be a member of the Houston group that developed DSP, LANs, and micros in the 80s and 90s. I live near Cambridge in the UK, have two sons, both have masters in engineering. One's just finished his PhD at Imperial.
Thank you, Teresa, for giving the complete background. Anybody else?
I'm Paul Brunk. I've seen you guys present a couple of times before. I'm a career HPC system administrator at the University of Georgia, US. I studied AI at graduate level 30 years ago. I've been system administration since then. I'm currently kind of re-entering as a casually entering data science, machine learning, see what has happened with the GPU revolution, and also want to expand my ability to facilitate onboarding AI researchers at our HPC center.
Thanks a lot.
That includes networking, CPU accelerators, the whole thing.
Sure. Thanks a lot. Anybody else?
I'm Hal Kelvin. And I've been doing this for 50 years. I learned basic and Fortran at a school you probably never heard of, Michigan College of Mining and Technology, bachelor's degree, but luckily they changed the name to Michigan Tech in Houghton, Michigan. So that's my formal background, but everything I've learned essentially on my own. I've lived in Silicon Valley since 1978, across from Stanford, and just being near the great centers on University Ave and walking over to Stanford, I learned a lot.
Okay, thank you. So let's keep moving. So before we get started, you can download a copy of the slides. This is the link I am showing here. Please take a look or just take a quick photo. That is the latest version of the slides you can have. And we also have a Slack channel. I think Amanda posted it, might be Aamir or Hari. Would you like to repost it so that everybody knows the link? They can post the questions there and we can monitor. Yes, Amanda also has posted. Yeah, sounds good. So we have a 3 hours window, a lot of things to cover, but we'll be going them in a very gradual manner. We also have very nice hands-on exercises towards the end. If some of you would like to really run some of the machine learning, deep learning algorithms. So we'll start with a very high level like outline saying what has happened in this field in the present, past, present, and future of AI, machine learning, deep learning, neural networks, what are the kind of the diverse applications. And then we'll go into a little bit more details to understand these kind of deep learning frameworks, how they are getting executed. And then we'll come to the need saying why we need this parallel and distributed training. Okay, because that is very important. Here we are talking at the Hot Interconnect conference where the state-of-the-art networks are being put together to design very large-scale systems. And all these machine learning, deep learning, data science are actually the big workloads for those machines. So then we'll go into taking a look at some of the distributed machine learning algorithms and data science using the Dask. And then we'll try to also bring together some of the latest trends, what is happening in the high performance computing, including the network interconnect, and try to understand what are the challenges in exploiting HPC technologies for DL, ML, data science. And then we'll go into much more details of specific solutions, like what kind of solutions, deep learning solutions are there, what are the machine learning solutions, what are the Dask solutions. And then we'll try to wind down, we'll talk about some of the open issues and challenges. And as I indicated, we have some hands-on exercises. We'll see, we have some an account. We actually at the Ohio State University, we have a GPU cluster with InfiniBand interconnect. We'll create accounts for you. We'll talk about those things. We have reserved it for the tutorial time so that you can actually go and jump in and then do some of the hands-on exercises. And then we'll conclude. So if you take a very broad look at the field, I know you might be getting information from all different places. The broad field is the AI. Okay, so that is the broad field. And within that broad field, there is a subfield, which is called the machine learning. And within that, there is even a smaller field is the deep learning. So we need to take these kind of a 3 levels aspects in mind. And especially if you see the machine learning, it has been there for many years. In fact, the AI, if you see here, it has been there from 1950s. In fact, not only 1950s, in many early days. The idea of the machine learning is that if you have a set of input, it could be images, it could be some data sets, it could be videos, anything, you are trying to do some feature extraction. And typically, a manual process is involved. Of course, nowadays there are some schemes where you don't need those. We'll talk about those. And then once you do this feature extraction, you do some classification so that once you have this model, then the next time any input comes, you can exactly trying to categorize. The question is, okay, can that model do the kind of inference? Now, what has happened in the deep learning, these 2 steps, feature extraction and classifications, are being combined. Okay, so the idea is that if we have a large input, the same, like whether it's images, data sets, can machine develop itself a deep learning model, and then we can use that model to for doing the inferencing for any new data. So that is the very high level perspective. So here it shows actually what has happened the milestones in the development of the machine learning, deep learning. If you below, you see these are the very famous names in the field of AI and gradually going into the HPC. These are all the heroes who have done a lot of work. Even if you go back, here you will see in the 1800s, people were talking about linear regression. Then close to 1940, if you remember, the Turing machine came. People started talking about electronic brain, perceptron. So gradually all these things, these terminologies have been there, these concepts have been there. So in fact, the 1960s to 70s, this was the golden age. A lot of new ideas came with respect to AI and machine learning. But the sad part was that there were not enough computing power to validate those kind of algorithms, to validate the solutions. So that's why this period is something like a dark age. People call it as like an AI winter. So people had ideas, but they were not able to validate. But all those things changed in the last 20 to 25 years because of the high performance computing, because of the evolution of the GPUs, very high performance CPUs. So this is where now you see the field has become very active, and the field of HPC and the field of the AI are in fact being very nicely gelled together. Okay. So if you take a look, I think since we are in the high performance interconnect conference, I'm sure many of you must be knowing about this top 500. These are the kind of the top 500 ranking of the supercomputers. It takes place twice a year, once in November in a US and once in ISC in Germany in June. So if you take a look at some of the very latest statistics, you can always go to this top500.org and get a lot of statistics. You will see a lot of these NVIDIA systems are being used. NVIDIA's, of course, some AMD's, all those GPU architectures are coming, Intel architecture is coming. And this has happened over the years. So currently, if you see like almost like a 163 out of 500 top HPC systems are actually using NVIDIA GPUs. Now, it is not just availability of the GPU. Another thing what has happened since 2014 are these different availability of data sets. So there was an ImageNet data challenge introduced in 2014. Every year also nowadays we see this Kaggle competition. They are also trying to provide a lot of open competition. So as these data sets are coming, as the people are getting exposed, different teams are working on, so the field is actually moving very fast. So it doesn't have to be the GPU. It is also have a CPUs are also there. We'll show some solution. If you have a very large CPU cluster, you can actually also run your GPU algorithms. So here it shows like what has happened. Like this is a world market. It's a little bit of older data, but it shows how the field has been evolving. Here we are, like starting from 2016, when people were talking the AI revenue in a very small manner, 2025, people are estimating almost $36 billion of market in the AI. And that is purely from a marketing perspective. But if you see the use cases, these are all the places people are using, like a contract analysis to object detection classification, object identification, geophysical feature extraction, text query of images, content distribution on social media, predictive maintenance, like the aircrafts, your cars, those kind of things. The field of medicine, that is also gaining a lot of traction with respect to utilizing AI techniques, then image recognition and all. But the biggest one is actually the stock market. Okay. I mean, people are trying to predict the financial market, things happening all over the world, and how exactly to predict so that people can actually, or the banks and all, they can actually properly invest and get the money. So this is a very broad perspective. Now, if you take a look at a little bit machine learning and deep learning, deep neural networks. So broadly, you might have heard of some of this terminology. So these are traditional machine learning. Okay, so it starts with supervised learning. That means if we have a lot of data sets, you generally come up with these algorithms, and then somebody is a human in the loop, the humans are trying to do some feature extraction, or they are trying to do some labeling. You take the data, do the processing, and then come up with a model. And then the next time the new data comes, you should be able to classify those properly. Of course, as the data set is increasing, it is becoming very complex for human beings to be involved in the labeling and those tasks. So people have come up with unsupervised learning. So here you can see that there is no human in the loop, but the machines themselves, the algorithm is trying to develop the model. Of course, there are some intermediate ones, semi-supervised learning. So that means you take some data, you label, not all the data, and use that as the baseline and then come up with the model. And the final one actually, which is getting also a lot of traction, is called reinforcement learning. So that means as you are developing the model, it's like an agent-based system, you take some feedback into account, whether the model is working correctly or not. Okay. And based on that, you correct the model. So that's how we'll go into some of these things in more detail later on, but we are just introducing the terminologies here. So then the other thing is the deep neural network. So this is the deep learning is coming. And this is how I'm sure in many papers and all, you would have seen a figure like this. So this is called a traditional, like let's say 3-layer deep neural network. There's an input layer, there is a hidden layer 1, hidden layer 2, and then there is an output layer. And all these are all we'll introduce. These are the nodes, these are the edges, weights, kind of things. And then you build this new neural network for a given application. Okay. And we'll see how to build those networks. But if you take a look at this, in fact, this is nothing new in our brain. I'm sure all of you would have taken some biology 101 class sometime. This is how you would have seen a biological neuron works. Okay. So that means we have a nucleus, we have some cell body, we have some dendrites, and these nucleus are connected, and there are some impulses. They are carried towards the cell body. Some kind of biological reactions take place, and then those impulses are carried away from the cell body to all the different kind of action. Okay. And our brain is designed with billions of such neurons. Okay. Now the question is on the right hand side, if you see, that is actually a mathematical model we are trying to use. Okay. The idea is very, again, similar. This is like a cell body, which is representing the nucleus. We have the different, these impulses are coming, and here we'll introduce some parameters like x, x0, x1, x2, and then the w's are weights. And based on these, there will be some kind of a summation will take place, and then there will be an activation function, which will be sending it to the output of the action. So this is what actually the field is trying to do, the deep learning. Okay. Exactly trying to mimic what is out there in our brain and how things are working. So if you build this kind of a model, again, just like human beings operate, there are two phases here. I used some of the word earlier. One is the training, and the another one is inferencing. So the training, the broad idea is that if you have lots of data, we talked about earlier, like it could be images, it could be videos, it could be even scientific data sets or medical data sets or even stock market data sets. We use those data sets to come up with this kind of a deep neural network. Okay. And there are some different phases. We'll talk about that, like there's some forward pass, backward pass, and we detect some error. There is an error, we go and then correct it. So like this, we go through a multiple iteration, and this is where this is a very compute intensive process. Okay. And this is where all the large HPC clusters are being used. And then once you have this model, then you try to do the inferencing. A new data comes, and then it actually goes through this model and then is able to say, oh, whether this is a human face or not in this case. Okay. And this is no different than how human beings also operate. So I give this very common example. If you think of a child, let's say the child doesn't know anything about the fire. I'm sure every child at some stage of his or her life would have put a finger in the fire. And then they get a sense saying, oh, this is hot. We should not be touching it. Okay. So once they do it first time, the second time, then after a few times, they know that, yeah, I should be avoiding the fire. So that means the human brain is being trained. Okay. So same thing happens. Like I'm sure all of us have learned driving at some stage of the life, driving, swimming. You take any example. Okay. So you make mistakes, you correct those, and then come up with a model. So that's what exactly this training happens. When we talk about this error, those are the mistakes. So we correct those mistakes and then go continuously and then come up with the correct model. So the challenge, what we'll be focusing here is that how to make this training faster. I'm sure all of you would have heard of ChatGPT. It has been designed like a billions of data sets, and using machines of multiple months. Okay. And even with the latest supercomputers, I mean, these were not possible like even 10 years back, 20 years back. Okay. So even though nowadays it takes it like several months, so the question is, can we even do it in few weeks? Or even some companies are trying to say they can move it from few weeks to few days or few hours. They also want to do online training. So this is where the computation and the deep learning and AI are all coming together. So with that kind of a background, we have a very quick demo. Might be Nawras, you can share your slides and show the demo. Just this is a very nice playground. Any one of you, if you would like to explain to this to your student, to your colleague, or even to your children, saying how this field is working, you can always use this demo. Okay. Nawras, go ahead. I'll stop sharing and then we'll spend a few minutes getting this demo, understanding this demo.
Okay, can you see my
Yes.
browser screen? Okay.
Mhm.
So yeah, so this is a neural network playground by TensorFlow. It's a nice visual tool to show how a feed-forward network, also known as a multi-layer perceptron, works. So in the middle console here, you can actually see the neural architecture itself. So by default, we'll have a simple network. It will have two input features, X1 and X2. Then we have two hidden layers. And a hidden layer is basically a layer that lies between the input and the output. And then we have the output itself. And if we look at it, it's basically a data distribution with two classes, orange and blue data points. And the objective of this network is to learn this pattern and be able to classify the data based on its Cartesian location. So let me start the training and see what happens. Okay, so we can see that the network converged to a solution after some time. The white line here represents the decision boundary. So basically anything outside this line will be classified as an orange point or an orange class, and anything inside it will be the blue class. And finally, we have so many different options to tweak. These are called hyperparameters. For example, we can change the structure of the network itself, add more layers or more neurons per layer. But also we have these other options like the learning rate and the activation, the batch size, and so on. And for different values that we choose, we get different solutions. We can also choose different data patterns and see how the training goes. So as Dr. Panda mentioned, this link is in the slides, so you can open it and explore it. And back to you, Dr. Panda.
Yeah, thank you. Thank you. So let me share back the slides and then we'll continue. So I hope that gives you a very, very high level perspective of how this training works. We'll of course go into much more details in the next few slides. So let's take a quick look at what are the kind of the applications. I just mentioned at a high level, but if you see here some concrete examples, like a credit card fraud detection. I mean, this is one of the very important applications. I know all of us at some point would have got a message saying from your bank saying, yeah, your credit card is being charged somewhere, and is it a correct charge or not? Okay. So of course, 20 years back, this was not possible. But nowadays, based on where we travel, how we travel, the banks have a lot of information. So they have built models, and let's say I give this my credit card. Let's say I'm trying to go to let's say UK and book a hotel there, and I'm giving my credit card. So the question is it really I'm doing it, or somebody else has stolen my number and is trying to make a booking? But then if there is a model which actually has the information that, yes, I'm traveling next month to UK and I'm making this booking, then that is not a fraud. So this is how the banks are building while being connected with all the different like the ticket agencies, different kind of hotel network. So they have information like how people are traveling. And then in spite of that, if it detects that, oh, there is a prediction that, yeah, 85% chance that this could be a possibility of a fraud, they block the transaction. And then you get a message saying, look, is just to validate on your iPhone or email, you get a message. And this is what is happening behind the scenes. We'll go into some of these K-means, GMM, PCA kind of schemes which are trying to do. There are many other areas. For example, the traditional scientific computing, if you go to Boeing, Airbus, or anyone like the Ford, Toyota, Honda, when they're doing a lot of designs. So all these designs have now, of course, we need high performance computing. They do a lot of simulations, but nowadays these are being guided by AI simulations, or the simulations are being guided, okay, through AI. So what does that mean? So let's say you have a big system, might have like a 10,000 components, and each component might have different degrees of freedom. So there are so many combinations you want to run the simulations. And many times you will see that in the simulation world, many combinations don't lead to good results. Now the question is, do you exhaustively do all those simulations? Because it will take weeks or months, or you can actually prune it based on the data or based on the results which you had from the previous simulation. So this is where AI is coming handy, that based on the previous simulation, you can say they are this parameter or these combinations are not yielding good results. So we can actually drop them. So that means then the entire overall simulation can actually be accelerated. Here it is an example, like let's say, think of like a bringing AI to the arts. So think of like a Picasso. Picasso's drawing have some characteristics. So now the question is, if I give a doodle, do we have a deep learning model which can actually print as if it would have been by Picasso? Okay. Of course, again, this is a very big challenge, and this is what also sometimes now these days the ChatGPT is trying to do in terms of text. Like if I give a paragraph, can that paragraph be modified like as if Shakespeare would have written it? Okay. And of course, there are a lot of ethical issues. I mean, continuously in the last several months, the community has been discussing that. But here we'll be taking a look at the challenge from a technical perspective, because this is a huge challenge. How do you take everybody's finger, the stroke in terms of the drawing and all are very unique, and can that be captured? Okay. Smaller examples like this, you can see, like let's say I go to Europe and trying to buy some things, cookies or chocolates for my daughter. I don't know the language. Then Google Translator comes to my rescue. Okay. Same thing happens here, like a self-driving car, as most of you know, this is the huge, big application. A lot of AI is being used there. So how the not only the cars, but trucks, transportation, all these can actually do the self-driving. In fact, the miniature version of these are coming. So this is a picture from the Ohio State University campus. So in fact, we have these small, you can say like a robot or small vehicles are actually going throughout the campus. So they have totally mapped the campus, all the sidewalks. You can actually order your food or lunch, coffee while sitting in your dorm. And then it actually gets from some cafe. And then here you can see it has some cameras, it has the things. It actually navigates just like the self-driving cars. Okay. And then it actually delivers at the when it reaches the ground floor of the building, it sends a text message saying, yeah, I'm ready. Then you come, put together a code, open it up and take your lunch, and then it moves. And gradually you will see these kind of things will have a big impact in terms of distribution of groceries, food, packages, mails. And in fact, 2 weeks back, I read in the state of Ohio, we have a lot of rural counties. So nowadays the drones are exactly using this kind of schemes to drop off medicines. Urgent medicines, or even collect medical samples, bring them to the main hospitals. So whatever was taking like a 2-3 hours of drive can now be reduced to like a 10 to 15 minutes, a drone flying and then getting things done. Same thing like the field of medicine. Here, I'm trying to show an example of pathology. You know, all of us go to hospitals, we take samples. Typically in the old days, they used to have glasses. They read the glass and then have some under the microscopes, they see what kind of symptoms or diseases you might be having. But if you think of like any hospital, I mean, over even a week, they get thousands and thousands of these samples. So the question is, can we actually build AI models using that? So when a new patient comes in, the machine will be narrowing it down and very quickly saying, X, Y, Z has this M, N, and P, so that the pathologist doesn't have to spend a lot of time. So we are not saying here that the machine is trying to give the final diagnosis. The pathologist will still be there, but it will try to cut down the time. And that's what we are talking here. So then with this kind of objective, if we now go into, let's take a look at a very concrete application area, which is like a computer vision. It has been there in the very early days of image processing. This is where all the convolution neural network or CNN had come. Now, if you take a look at this kind of picture, so let's say we have a picture like a bird, and how do we classify it? Okay, so this is where actually what happens, it goes through each and every pixel. And from those pixels, we want to understand, like, is it a bird, it is a sunset, it is a dog, or it's a cat, what that exactly represents. Not only that pixel, but in the context of that figure. Okay, and then this is where you do a lot of processing. And those kind of processing actually is, sometimes you must have heard of, called a convolution operation. This is like our basic linear algebra class we would have taken at some times in the high school. So you're trying to have like this kind of a left input, and using some filters, you actually come up with the results. And over the years, people have developed all these different kinds of filters, and each one has some property. Okay. So here on the right hand side, it's trying to show how the actual convolution is happening. And if you see the convolution, these are all mathematical operations. So it's a huge amount of computation involved to do this kind of convolution and then abstracting the results up. So this is a very concrete example. Like if I have like a data sets like this, let's say the 0 is darker or darkest and 10 is lighter. How do we detect, how does the machine detect from the data sets that there is an edge here? Okay, so this is the actual image, and we are representing it by data, and we want to detect this edge in an automatical fashion. So to achieve this, there is actually a filter. So if this is the filter, you do the convolution, you will exactly get this kind of solution, and then the computer in a mathematical model can actually identify there, look, there was a transition happened here. And this is how like the computer vision people have been working over the years. This is a very simple example of a vertical edge. You can get a horizontal edge, you can get a circle. So once you get all these kind of shapes, then you try to build the feature map and then come up with the complete description. So I'll end this section. I'm sure all of you are familiar with this figure. Can somebody quickly say what this figure is or picture is? Anyone from the attendee?
R2D2 and C3PO.
Yes. So now the question is, if this is the picture, and I want to take it through a deep learning training, I can use a lot of filter. Like there is a filter here, very simple, called Sobel filter, and I can do the convolution, and you see the right hand image. Okay, it captures all the edges. Okay, so this is a kind of a abstraction of your feature map, and then I can take it and do the further kind of computations. Okay, so that is the power of all these filters, and of course this is where a lot of computation happens. And in the next section, we'll see how these things get linked to common frameworks, like I'm sure all of you would have heard about PyTorch, TensorFlow, and all. If you go below, this is where you see all these kind of computations are happening. So I'll close this section here. Then Aamir will take over. But if there are any questions, I'll be happy to answer here. Are there any questions in the Slack? Or you can directly ask the question. Either way is fine. Okay. And those who joined late, the slides, copies of the slides are available. I think it was posted. If those of you who joined a little bit late, we can again post the link. So you don't have to write down or take photos or any of those things. Yes. Aamir, please proceed.
Yeah. Thank you, Dr. Panda. So in the next section, we are going to talk about some of the machine learning and deep learning frameworks. So I think we have been motivated why this is important, some of the application areas, but for your own specific application, how could you utilize, this magic for your own application. So here is an overview of the MLDL frameworks and hardware architectures and, distributed, training. So obviously the idea of MLDL frameworks is that it will hide, most of the complicated mathematics that's going on in the background. There are some, obviously on the right-hand side here, we have, the mathematical equation of logistic regression. If we are doing low-level programming, this is how we are going to write it. And this is basically the graph that's being generated. But I mean, if you're a computer science person, you might be interested in going until this kind of detail. But if you are from, let's say, an application area, then maybe, you don't want to worry about all these details. And that's where the MLDL frameworks come in, because they, hide this complication from end users, and they're able to use or utilize deep learning in an easy way for their own applications. And another advantage of these frameworks is that, this is going to utilize the hardware, facilities in processing elements available to you. So for example, maybe you have an application where a single GPU or a many core CPUs on your laptop is not enough. So how do you utilize, let's say, how do we combine multiple computers and use them as a single computer for training large models? So, in this context, that's another place where these MLDL frameworks shine, and they allow us to utilize, parallel, they basically enable parallel and distributed training of deep neural networks. And also, as the field is progressing, people are also building dedicated hardware architectures for processing DNNs. One of the famous example is, the TPUs from Google. And essentially, you could utilize all of this in a very easy to use way using MLDL frameworks. So what are the machine learning frameworks available today? So when I'm using the word machine learning here, I'm talking about the classic machine learning that typically doesn't involve deep learning or DNNs. So if you're, let's say, doing, things like k-means, simple, linear regression, logistic regression, you have this option of using this scikit-learn, which is a very popular and old machine learning framework. But this doesn't have support for GPUs. But let's say if you're trying to use, your application is written in scikit-learn and you want to use GPUs for compute intensive applications. So QML is one option. This is a project from NVIDIA. So we will, talk more about this. And then, there are some specialized gradient boosting libraries out there as well. For example, like XGBoost. So these can also be utilized for writing your own machine learning algorithms. However, the most important thing here is, DNNs and deep learning, and the most popular frameworks available today are, the top two here, Google TensorFlow and Facebook, Torch or PyTorch. So historically, there have been other frameworks available as well. So for example, like Caffe, CNTK, Chainer, Nirvana, Onyx is another one. But, if you're learning deep learning today, and so, these are the two that you need to worry about, Google TensorFlow and Facebook PyTorch. So first we talk about Google TensorFlow. So although it says on the slide here that this is the most popular framework, I'd say, this is one of the, popular ones. And this is, open source by Google. The historic version of the Google TensorFlow was dist belief framework. And this supports execution on all parallel architectures, including many core CPUs, GPUs, TPUs, and even, mobile devices. And the API for Google TensorFlow has, initially they had TensorFlow 1.0 that enabled, lazy execution and had this, concepts of sessions and estimators. But in TensorFlow 2.0, it enables eager execution. And this is, the approach that's invented by PyTorch as well. And this is the GitHub URL for TensorFlow. And this, remains one of the popular frameworks today. But I'd say, the most popular one today is Facebook, PyTorch, Meta now. So, this is basically a newer version of Torch that was originally written in a programming language called Lua. But, the adoption wasn't widespread. But then, PyTorch is a Python adaptation of Torch, and Meta remains the biggest contributor to this, but this is an open source software. And, the key selling point here are ease of expression and this so-called define by run approach that basically allows, debugging on the fly and is a really performant method of training neural networks. So again, as I said before, there are many other DL frameworks available as well. Cafe, Keras. So Keras is a higher level API. This lets you define, your deep learning model in a higher abstraction, and then you could utilize a variety of deep learning frameworks to execute your model. And then others include Theano, Blocks, Intel Big DL, and there are some other specialized ones as well. For example, this LBAN, and the list keeps growing essentially. Every I would say week that we have new papers coming up that talk about new and new frameworks. So here are some of the statistics about ML and DN frameworks. So this is a somewhat dated slide, but let's focus on the top graph here. And this basically shows the cumulative GitHub stars for an AI library. And then we have a clear winner here. And this top one here is basically the Google TensorFlow, right? And then at the bottom here, we have other variety of DL frameworks. But if we zoom into this, crowded part, and the bottom graph here is the zoomed in version of this crowded graph, we see that, there is a clear, winner amongst this crowd, which came about in 2017. And then towards the end of 2019 was, perhaps the second most popular framework, and this is essentially PyTorch. And in the academic circles, we have this, it's a common sort of understanding that PyTorch is more widespread or more widely used in the academic community than TensorFlow. It's because, making additions to PyTorch is much more simpler than making changes to TensorFlow, and academics essentially, would like to optimize certain aspects, performance evaluation, characterization, and those kind of, research ideas. Those are easy to execute with PyTorch than compared to TensorFlow. So here are some more statistics as well. So for example, another, criteria that, we'd like to sort of gauge these two frameworks is the model availability, right? So Hugging Face is one of the popular model repository out there today, which has trained and tuned state-of-the-art models. And if we look at, the left-hand side figure here, if we pick the top 30 models on Hugging Face, we'd see that, all 30 of them, we'll find an implementation of them in PyTorch. But, only PyTorch, there is no model that has, no implementation in PyTorch. And if we, go and look for both implementations, then we have around 18, whose implementations are available in both PyTorch and TensorFlow. If we look at the number of support for number of models, Hugging Face, out of the total models available, we will see that, a lot of the models there are, PyTorch only. So, almost 85% of the models are PyTorch exclusive. That clearly shows that, the community is, investing heavily in PyTorch. So another way to look at this is the research paper. So for example, in 2017, this orange sort of shaded area here is TensorFlow. And then this, this other color, the magenta color, is basically the PyTorch. And you can see that, the PyTorch adoption is, has increased significantly from around 5-10% to around, 77% in 2021. So, 80% until, 2021. So obviously there is, a lot of adoption of PyTorch clearly. Another way, so this is a website called Papers with Code. So they keep track of the latest papers coming out, and these papers are not just theoretical papers. They have a GitHub repository available there with them as well. And clearly the portion of PyTorch, which is this middle portion here, has significantly grown over the last few years or couple of years. So with this now, I'll move to the next section of the talk, which is overview of execution environment. So we have talked about the MLDL frameworks, but in this section we are going to talk about that the DL frameworks is, if you look at the whole stack which is being used to train neural networks, then MLDL frameworks is just one piece of the puzzle. It's a very important piece of the puzzle, but it's just one piece of the puzzles, right? So for example, today, we are looking at the large language models. They cannot be trained on a single GPU because they have so many parameters. They consume so much memory that they will not fit in the memory of a single GPU. And only, before 2014, there was no MLDL framework that had support for parallel and distributed neural network training. So, one very important factor now is, what kind of parallelism is supported by the MLDL framework that you're going to utilize. And we are going to talk about this aspect of MLDL frameworks in significant detail in this tutorial. But this is a very important criteria that we are going to look at. And then another thing is, if we are, let's say, going to engage in distributed training where we are going to use multiple computers, then one very important aspect of the overall stack is the communication library and the communication stack which is being utilized. And we have a variety of options available like Horvath, MPI, Nickel. So we are going to talk about what are these, but the overall performance of the DNN training is going to rely heavily on the performance of these communication libraries. And then on the other side of the spectrum, there is, as DNN training or deep learning has become an important workload, we are seeing that a lot of hardware architectures are also emerging. So for example, Google TPUs, also smartphones, self-driving cars have their own frameworks. People want to run run inference in web browsers. So all of these MLDL frameworks, they have to support a variety of hardware, ranging from Google TPUs to web browsers to smartphones. So conventionally, we GPUs and CPUs have been used for DNN training, and people have tried to basically look at what's the which framework performs better for certain types of DNN models. But obviously there is no one answer for there's no generic answer, because it typically depends on what model is being trained, what's the application area, what's the underlying platform. And then, if we look into more detail, it even depends on the software stack, what numerical library is being used to perform the mathematical operations that are typically done while training DNNs, and communication library. So we need to look at everything from a holistic viewpoint. So in this context, we published a paper in ML-HPC, which is a popular workshop at SC. And here is the right-hand side figure here shows what kind of software stack is being used to train DNN models. So for example, at the top we have DL applications. So we could be doing image recognition, speech processing, language processing, and then we have all these DL frameworks, PyTorch, TensorFlow. They support different mathematical operators like convolutional networks, and then they make use of certain mathematical library. So because at the end of the day, DNN training boils down to, matrix or matrix vector operations. So, it depends a lot on, your underlying hardware. First of all, has it got some special instructions to, let's say, optimize matrix multiplication or matrix operations. And then it also depends heavily on the mathematical library. So for example, this math kernel library or cuDNN or cuBLAS. So, just by changing one version of the library. So for example, if you're not using the latest version of cuDNN with, let's say, PyTorch, this could easily result in suboptimal performance. And, when you're looking at doing performance evaluation or characterization, so obviously we need to look at the whole stack and make sure that you are utilizing the latest version, and as well as using the most optimized, software stack or individual pieces of the libraries that are available out there. Right. So with this, I'll hand this over to my colleague, Nawras. I'm happy to take any questions if you have any questions or comments.
Are there any questions? Yeah. Aamir, we are telling something. Are there any questions on the Slack?
Okay, so I can check Slack.
I'm checking also. Or otherwise, people can just post it here or unmute themselves and ask questions also. It will be good to have going on an interactive mode here.
One of the topics, my name is Paul Boyle, I'm the CEO of Daedalus. One of the things that's coming up now across all of the conferences I'm talking about is that there is a revolution happening now in computer architecture. Computer architecture has been stagnant for maybe 2-3 decades. And what I'm realizing is that deep learning and different communication patterns that are occurring are really causing all of us to kind of like rethink from first principles, what should computer architecture look like?
Yes.
And it's interesting because this is kind of happening at the same time as the chiplet revolution, where we're looking at a completely repackaging of how chips and chiplets and modules are put together. Can the speaker address that in terms of what they understand how computer architecture should change in their communication structures to support deep learning?
Yes. So Paul, nice. Thanks to know that you're attending here. So you put a very great question. So in fact, if you see what is happening, especially for all these AI workloads, as we showed, the below is actually those kind of convolution operations, those kind of complex operations are taking place. And this is how actually, if you go and take a look at the NVIDIA GPUs and all, even Google Tensor Processing Unit, so they're creating all these tensor cores. So traditional CPU architecture, we have just dependent on load, store, and then integer or floating point operations. But here it is going to the next step, like can it do a matrix operation or matrix vector operations? Okay, so those are coming like an instruction sets, and any architecture which can try to accelerate those operations will demonstrate big performance on the for the end application. The other thing is happening. The traditional CPUs have, especially geared towards scientific computing, has always focused on floating point performance, whereas these new workloads, the data is like images. These are like videos. These are integers. So there is a change is also happening. People are gradually de-emphasizing the floating point. Instead of doing 32-bit, 64-bit, people are coming to 16 bits, even 8 bits kind of things. And this is where you see when some of the top 500 numbers are being posted, instead of traditional HPL, those are the scientific workload. Now people are presenting in the AI workload. So they are actually using this 8 bits, 16-bit kind of things. So these both the fields, whether it's like architecture or HPC or AI, they are rediscovering themselves, saying what is needed for the next generation AI workload. And And then I'm sure like you are familiar with the smart NICs and all those things. So that is happening in the other directions. In fact, we'll talk something like that in the afternoon. I'll also be presenting another tutorial on the high performance network, and we'll bring the smart NICs. And here also later we'll see that a lot of this parallel and distributed training requires all reduce or all to all. These are collective operations. And any machine which can do all these collective operations the best possible manner, they will give you the best performance. So this is where even the field of networking, the traditional interconnects and all, starting from InfiniBand to even Ethernet. So everybody is focusing on not just point-to-point communication, but a lot on these collective communications. And whether you do it in the in-network computing or you offload them to a smart NIC, if you can implement your all-to-all or all reduce in the best possible manner, you will get very good performance and scalability for these AI workloads. Okay. So I hope that answers your question. We'll go into some of these things later in this tutorial.
Good, thank you. Yes, that answers it very well. Thank you.
Thank you.
One of the interesting questions here is, okay, what is all reduce? Is it kind of like just like a map reduce?
No. Just wait for in the next section. Actually, we'll go into more of these. You remember I talked about these errors and all. So that's what you will see, some examples. Okay.
Thank you.
Yeah, please wait for another 10 slides. You will get the answer. Okay. Yeah. Any other questions from anybody else? Okay. Nawras, you can get started.
Okay. Thank you, Dr. Panda. So next in this section, we'll cover some basic background and essential concepts about DNN training. And then we'll look at some of the parallelization strategies that will not only help us train DNNs faster, but also enable us to train large DNNs that are too big to fit in the memory of a single machine. So this is an example of a 3-layer deep neural network, a feed-forward network. And this consists of basically one input layer, 2 hidden layers, and 1 output layer. So we don't count the input layer. We just count the hidden and output. So that's why it's 3 layers. And then each layer consists of neurons. And we can think of neurons as small mathematical functions. In fact, we can think of the entire network as one big, very complicated function with many parameters in it. And the goal of the training process is to adjust these parameters so that when we give it an input, it gives us an accurate prediction. So that is the training process, basically. And in the training, we have 2 main phases, the forward pass and the backward pass. In the forward pass, we feed the network an input, X, and then we propagate it across the layers. So X here is fed, then it's multiplied by the weights, W1 and W2, and we do this for the next layer and the next layer until we get an output. The output represents a prediction. So let's say we feed like a cat image and we want to give a prediction. Is it a cat or a dog? Based on a prediction, we will calculate an error or loss. So let's say we predicted a cat, but it's a dog. So our loss is high, meaning we need to adjust our weights in the network. So based on that error, we do the backward pass, which propagates the loss, right? So now we have not only error at the end, but we have E7, E8, E3, E4. These are the errors for the rest of the layers. And based on that error, we apply a weight update so that in the next time we see a similar input, we give a more accurate prediction. So the training process, the forward and backward pass, it involves pretty complicated math. Let me try to give a high-level definition of what's happening. So in a simple network, we have X, the input. Theta 1 is basically the weights. And then we have an activation function. This can be something like ReLU, sigmoid, or tan H. So this activation functions applies a nonlinearity to our neurons, and that helps in learning on linearly inseparable data. So it will basically improve the network. And then to calculate the activation, we basically apply this activation function G, and then it's just a linear combination. It's the theta, the weights, multiplied by X, the input. And we do the same for the next layer. And then in the backward pass, to adjust the weights, we need to calculate the gradients. So we need to basically calculate the derivatives of these activation functions and then propagate the error back. Luckily, most DL frameworks will give us a one-line implementation of all of this. So you just call model.backward and it will do all the complicated math for you. Even if you want to define a new architecture with your own layers, and like you want to define the number of neurons and then the different types of layer, maybe convolutions or multi-head attention. So all of that will be taken care of by the DL framework. So some important concepts for DNN training. I mentioned a learning rate in the demo, and the learning rate basically decides how big of a step do we take towards the solution after we calculate the gradients. So this is like an iterative process, right? We look at many samples and we try to learn from them. But like after we see each sample, or let's say a batch of samples, how big of a step do we take towards the solution? So we can think of J of theta as the error function, okay? So how far are we from the correct predictions? And we want to minimize that error. So we want to basically find a minimum point. So if our learning rate is too low, we're going to take too small of steps, and then we need many iterations to do the training, and then our training will take very long to converge to the solution. If it's too high, we'll be jumping back and forth, and we won't converge to a solution because our steps are too big. So the learning is happening maybe too quickly. But if our learning rate is right, then we can swiftly reach to the minimum point with the minimum number of steps. So this is something that we need to keep in mind when training a network, especially in a distributed setting, because we need to scale the learning rate. And also there are ways to optimize this. So we don't always have to do it manually. We can use advanced algorithms to do it for us. And then the next concept is the batch size. So batch size determines how many samples do we feed a network at a time. So there are different ways to do it. The first way is called batch gradient descent. And in this approach, we feed the entire data set. So let's say we have a data set with maybe 1,000 images. We feed the 1,000 images to the network. We do the forward and backward pass, and then we apply the update. So one drawback of this approach is that, okay, maybe our training step will be too big because we're relying on the entire data set, but also this will take a long time to finish the whole data set in one step. So the next approach is called stochastic gradient descent. And in this approach, we take one sample randomly from the data set, and we apply the forward and backward pass, and then we apply the update. So we pass the entire data set, right? We take a sample randomly, we train the network, and then we do the same for the next sample and so on. And if we pass the entire data set, this is called an epoch or an epoch. One drawback of this approach is that, okay, maybe our training steps will be too small, but also we are not fully utilizing the hardware resources, because if we train one sample at a time, we're missing like a huge opportunity to parallelize our application. If we can train multiple samples at the same time, then we can utilize many GPUs. together. So in between, there is a solution called mini batch gradient descent, and we basically divide the data set into multiple mini batches, and then the batch size can be like a multiple of 2 usually, so 32, 64, 256, and so on. And then we train the network on this batch, so like 64 images at a time, forward, backward pass. We do the update, and then we move on to the next batch. So in this way, we can do parallelism, so we can train multiple images or samples at the same time. But also, if we find like the optimal batch size accompanied by the optimal learning rate, then we converge quickly to the minimum point. So these two are things to tune when we train a network. Okay, is there a question in the chat? Share the slides link. Okay, so the need for parallel and distributed training. Why do we need distributed training? Basically, deep learning models are getting. Sorry, is there a question? Okay. Okay, so why do we need distributed training? We are getting larger and deeper models. So something like GPT or ChatGPT, these are very huge models with billions of parameters. And they require a lot of memory and a lot of computation. And they may not fit in the memory of a single GPU. Furthermore, the data sets that we train on are very huge. So we have many, many data samples. So the training will take very long to finish. And one solution is to do multi-GPU training. So if you have one node, one computer with multiple GPUs on it, you can distribute the training. So this is one solution, but multi-GPU training is limited to the number of GPUs that you can host on your machine. So maybe 8 to 16 GPUs maximum. That's why we need multi-node or distributed training. So if we have like an HPC system with many nodes on it, we can leverage that for accelerating the training. Okay. Now, how do we choose the model size? We said that the model is getting bigger, but the data size are also getting very large. Usually, larger models lead to better accuracy, and if you have more data, we also achieve better accuracy. And if we have like a single node, then a single node would be very good if we have a small model and a small data set. But if we have, let's look at the extremes. If you have very large model but small data, we'll need multi-GPU to train it, right? Because the model is big, but we might be overfitting, right? So we are basically memorizing the data instead of learning it. So if you see new data, we're not gonna get any good accuracy. We're only training a model to do very well on the training data set, right? And on the other hand, if we have large data but small model, then we are underfitting. So the model does not have enough parameters to learn from the data. So we have like complex data set with a lot of features, a lot of classes in it. A small model won't be able to handle it. So if we have a large model and a lot of data, then we need distributed training to speed up the training and also to resolve memory limitations. This is how overfitting and underfitting look like. So we said overfitting, if you have large model but small data, you're gonna memorize the data and not learn. So this is what, let me use the laser pointer. This is what overfitting looks like. We are basically memorizing the training data set. So if I give this model a new data point, it will perform poorly. If we're underfitting, then our model is too simple. We are not learning the complex relationship that is present in the data. But if we choose the right model for the right data set, then we have this balanced learning. large batch sizes are very important in distributed training because the larger the batch size, the more parallelism you can have. So if you have very large batch size, let's say maybe 16K, 32K, then you can distribute these samples across many machines, right? But so it's good for speed and scalability, but it's bad for accuracy. So the larger the batch sizes, this is training a model on the ImageNet data set, and this is the top 5 validation error. So the lower is better. And we can see after some point, if we increase the batch size further, we start losing on accuracy, or basically the error increases.
We are going to lose the accuracy.
Okay. So this isn't like an ongoing research question, right? The large batch training, and there are some ways to resolve it, but also this is something to keep in mind when doing distributed training. Okay, can I go to them? Okay. This is how mini batch gradient descent look like. We said that we take the entire data set, we divide it into mini batches, and we feed one batch at a time to the model. And then we get the output, and based on that output, we calculate the error, we do the backward propagation, and we update. The drawback of this approach, if we have like a very big data set, 1 million images, the training will take forever to finish on such a big data set. And the solution, as we mentioned, is to distribute this workload on multiple machines, utilizing supercomputers. How can we do that? How can we achieve this parallelism? There are several techniques to do it. Perhaps the most popular one is the data parallelism, where we take the model, the deep learning model, we replicate it on different machines. So in here we have 4 machines, and we have the same model replicated, and then we feed each model different data samples, and we do the training, and there's some sort of communication involved in here that we'll discuss in the next slide. And then the next approach is model parallelism, where we take the model and split it across the different machines. And this is very useful when the model is too big to fit in one machine. But the performance of this approach might be not very good, the scalability compared to data parallelism. So that's why we have hybrid parallelism, where we combine both of these approaches. And we'll talk about model and hybrid in another section in this tutorial. But let's take a closer look at data parallelism. How can we implement it? So this is what data parallelism looks like, the implementation of it. So we have a data set, okay, and we divide this data set into mini batches. And then in this example, we have 4 GPUs, okay, GPU 0 to 3. And on each GPU, we have the model, right? We said we're going to replicate the model. So these are the model parameters. And then for each GPU, we're going to do the forward and backward pass separately, right? But at the same time. And then we end up with the local gradients. So like the gradients will tell us how should we update the model. But now we have different gradients for each model. And we don't want to train 4 different models. We want to train one model on these 4 different machines. That's why we need MPI or reduce. So there was a question about or reduce. Or reduce will basically take these gradients from each machine, from each GPU, and it will aggregate them. So or reduce will do some sort of a calculation, right? It could be addition or like subtraction or multiplication, but it will basically take parameters from these different processes, and then it will add them together, and then it will broadcast them back to the processes again. So now basically we're going to take these local gradients from all the nodes, we're going to do all reduce, which will aggregate them, and then we'll distribute them back to these 4 GPUs. Now we have the same global gradients on all machines. Only then we can update the parameters. And now this is a loop, this is an iteration, an iterative process. So as we said, we need to do it many, many times to train an accurate model. So you can see that all reduce will be called many times during the training. That's why if we optimize all reduce, then we optimize the overall performance. Okay, so that is it for the distributed DNN training. Are there any questions about this?
Thanks, Karen.
Okay.
May I ask a question?
Yeah, sure. Go ahead.
So when you're like training a bunch of pictures recognizing cat, that's a very clear yes. You know, somebody gave the answer that this is a yes or no, so they can correct. But for something like ChatGPT, how do they grade something like that?
Yes, so, yeah, that's a great question. So ChatGPT, or let's say large language models in general, the training consists of 2 phases. The first phase is called like self-supervised. Okay, so basically we give the model a huge data set, a huge corpus of text, maybe Wikipedia, right? And then we give it articles from Wikipedia, and then we mask some words in it. And then we ask the model to give a prediction for these masked words. If the prediction is accurate and close to the correct word, then that's good. If it's not, then we adjust the model weights. We also do sentence completion. So not only masking, but also sentence completion and ordering. So that's the self-supervised part. And then we have the fine-tuning part. And in that part, we can feed it like a labeled data set, like the question answering data set. So we have our input is a question and our label is an answer. And then we rate how the model gave the answer. Is it close to the correct answer? And based on it, we adjust the weights. So
that's a fantastic answer. But for the second part, so the first part is all automated. You can just find,
yes,
like all, language, just paragraphs out of the internet. The second set, is that hand tailored?
Yes, it is. Or you can also scrape it off the internet. So let's say you have a forum, or let's say Stack Overflow. Stack Overflow is a bunch of questions and answers, right? So you can form your data set so that it is labeled.
Oh, excellent. Thank you very much.
Yeah, sure. Great question.
Any other questions from anybody? If not, Aamir, you can get started.
Sure. I'll get started. So with the next section, which is distributed machine learning algorithms. So just the way we were talking about a neural network being executed in a parallel and distributed way, so it's possible to utilize that for machine learning algorithms as well. So for example, on the right-hand side at the top right, we have a bunch of points given to us. And the task here is to cluster these into, these points into clusters. So in this case, the data set, we are clustering them into 3, red, blue, and green clusters. So for this purpose, we have actually we could, if we are executing this in parallel, we could, divide the input number of points into 2 sets. So for example, here we have node 0 and then we have node 1. So then this basically becomes a similar problem. So, what we are basically doing here is that all the processors, so in this particular case, in the bottom left figure, we have 3 parallel computers working on their own local points. And then they're basically calculating the mean of, the 3 clusters that they are, tasked to actually identify. And once each of the system or each of the processor has found the the local centroid of the cluster. We basically engage in an all reduce operation to find out the global centroid for red, blue, and green clusters. So in this case, the data which is being exchanged is just dependent on how many clusters we are trying to find. So which basically means that it's not as compute intensive as DNN training, but still there is, all reduce operation going on, which is helping us find, the new global location of the 3 clusters at every iteration of the algorithm. And because this not a lot of communication is happening here, it's, we have seen in practice that parallel implementations of k-means algorithms would, scale in a linear fashion on a parallel system. So in this case, we are looking at numbers on the Hopper system, and then we have, this blue line corresponding to 32 dimension, red line corresponding to 64, and green line corresponding to 128. So if we again, we have discussed this before. So if you're trying to run, machine learning algorithms in a parallel and distributed way today, so, the first library that you would typically use is scikit-learn, but this doesn't support GPUs. So, QML is a good option. This is a project from NVIDIA. This basically provides support for GPU execution as well as parallel and distributed execution. If you're relying on, let's say, gradient boosting algorithms, then, XGBoost is a great library. This has support for parallel and distributed execution. And, there are other specialized machine learning libraries or frameworks out there as well. So moving on to the third use case that we are discussing here, which is data science using Dask. And data science basically means that, so this is basically a pre-processing step to DNN training. So you're given a bunch of data, let's say, and you want to, let's say, filter that data. For example, you're given a big, Excel data, and you want to, let's say, filter this based on some key values. You want to look at particular columns, particular rows. So, a technology like Spark and Dask, they are basically, they will help you to do that kind of pre-processing of your data. And once your data is pre-processed, then, you could think about using them in, let's say, DNN training or machine learning to basically build your models. So one technology that stands out here is Dask, and this is a popular task-based distributed computing framework. And the good thing about Dask is that, the same Python program that you write for your laptop, the same program would be able to execute on supercomputers or high-end systems as well. And under the hoods, this builds a task graph which is executed lazily on parallel hardware. Another strength of Dask is that this extends existing data processing libraries like NumPy and Pandas. So, I mean, if you're a Python programmer, you're already, most of the Python programmers are already used to NumPy and Pandas, APIs. Dask Distributed is the library that supports parallel and distributed execution. And today, if you're, working on Dask, so this will give you 2 particular communication devices, TCP and UCX. And from our own lab, we have developed an MPI-based communication library, and we are basically going to discuss this in more detail later in the tutorial. And for the Dask, the distributed execution model is like this. So, the central entity here is a scheduler, and then we have a bunch of workers which basically come up, they connect with the scheduler, and together the workers and the scheduler, they become a Dask cluster. And, when now it's time to execute user code from the client, we start the client process, submit the user job, and this client contacts the scheduler and, conducts data analytics on your input data in a parallel and distributed way. And this is what is enabled by Dask. Right. So with this now, I'll hand this over to my colleague, Hari, who'll talk about, high performance computing architecture. If there are any questions, we are happy to take any questions. Okay, so over to Hari, and he'll, go into details on the computing architecture.
Thanks, Aamir. Let me just open up the slides. Give me one moment.
Absolutely sure.
So while we are waiting for Hari, can I ask a quick question?
Yes, absolutely.
Yeah, so maybe this is for Nawras and Aamir, both of you. So how much time? So we know that all reduce takes a significant chunk of the time, but aside from all reduce, how much time does it take to move the data from initially from the file system to the GPUs, and what is the trajectory, or what are the best practices there? Is the data resident on the file system, and then you periodically move the batches to the CPU and then to the GPU, or and how is CPU used in this in this type of workflows?
Okay,
Go
so
ahead, Nawras.
yeah, I can answer this question.
Go ahead.
So yeah, that's a very good question. So basically, it depends on the deep learning framework. But let's take PyTorch for example. In PyTorch, you have what is called data loading workers. So those are processes that are run on the CPU, and you can assign many workers, right? So if you have like a multi-core CPU, you can run many data loading workers, and
So
the
these
workers
are running on processes or on threads?
threads.
I see.
Yeah. And then yes, you have your data set on the file system, and while the training is happening, these threads will be basically queuing the data from the file system into the host memory or the GPU memory. And it will also be performing data augmentation and data like pre-processing, right? So it's not only loading, but it's also augmentation. Now, your question was like, how like what's the percentage of time that is required to do this process? Ideally, you can completely overlap this with the training, right? So while the training is happening, the CPU will be doing the data loading, but that is like dependent on many factors, like the CPU architecture itself. Is it powerful enough to support, let's say, 4 or 8 GPUs on one node? And it's also dependent on the size of the data. So if your batch size is very big, if your image size is very big, then the data loading will take longer, the pre-processing will take longer. And finally, it depends on the model size. So if your model is big, then it will take long to train on the GPU. And if you have enough time, then you can do the data loading. But if your model is small, then you need to load the data faster from the file system. I hope that answers the question.
Thanks. So it is implicit that you need fast connections to a file system.
Yes, you definitely need fast. So like if you use the Scratch file system, so if you have like a Lustre file system compared to like an SSD on your node, then your performance might be different in some situations. So like, yeah, you need fast connection to the file system.
Thank you.
Sure. Thank you for the question.
Yeah. Thanks for the question, Sayan. Appreciate it. So sorry for the slight delay. So far, we have looked at various machine learning, deep learning frameworks, how they are executed, why you need parallel and distributed computing, and some solutions that use distributed computing in the machine learning as well as the data science side. Now, that is the demand side. Let's take a quick look at the supply side and see what are driving modern high-performance computing architectures. So currently, you have multiple drivers. You have multi-many core processors, high-performance interconnects, and I guess most importantly, accelerators like GPUs, which more or less form the heart of most compute operations in modern deep learning, machine learning, as well as data science workloads. And as we just discussed, your I/O or your file system is also pretty important, because if you don't have a high-performance file system, you're not able to keep these like high-end devices busy. So what we'll do in this section is very quickly and at a very high level talk about the various hardware architectures and the corresponding communication middleware enabling high-performance distributed deep learning. Under the hardware architectures, we'll be looking at various interconnects. Well, this is hardware interconnects, so I'm sure all of you guys are very familiar with all of these things, as well as the processing side. And on the processors, we'll be looking at certain processors which have come out recently in the market, geared towards machine learning and deep learning kind of workloads, and unlike the traditional scientific computing workloads. Now, if you look at high performance interconnects, there are several: InfiniBand, OmniPath, Slingshot, RDMA over Converged Ethernet. So they are generally characterized by three important, let's say, features or hallmarks. So low latency, high bandwidth, they are basically no-brainers. The third one is what we call as low CPU overhead. So typically, if you look at any HPC application, communication is something that the application developers have to do, not something that they want to do. So ideally, if you have a like fabric with zero latency and infinite bandwidth, they are really, really happy. Unfortunately, that's not possible in reality. And now on top of that, let's say if you tell the application developer that he or she has to sacrifice 15 or 20% of the CPU cycles to progress communication, it's even worse. So from that perspective, low CPU overhead is an important aspect of high performance interconnects, and most high performance interconnects listed above have some sort of hardware offload capabilities to offload the process of communication from the CPU. And many of the systems in the top 500 have these interconnects. Now, briefly, this is how one particular instance of a high performance interconnect, InfiniBand, has evolved over the last couple of decades. So currently we are at NDR, which is 400 gigs. So these products are available, at least to select people out there. And the next generation is going to be like 800 gigs. And the assumption is that in the next 5 or 8 years, we'll be crossing the terabit boundary as far as networking technologies are concerned. So with that brief foray into interconnects, let's take a look at some hardware which have been introduced over the last 5 to 10 years, specifically aimed at DNN training and inference. So one such solution is the tensor processing units, or TPUs, from Google. And if you look at a TPU, it's a CISC style instruction set, and systolic arrays, which were in use several decades ago, forms the heart of the multiply unit. So these solutions are available to you on the Google Cloud. And if you take a look at it, most of these fine-tuned hardware for deep DNN training and inference are available on some or the other cloud platforms for you. The intelligence processing unit, or IPU, is another such example from Graph Core. So there are two components to it. They have the IPU and the corresponding popular graph processing unit. And when it came out several years ago, they were able to demonstrate at NIPS that the IPU with the corresponding communication middleware was able to significantly outperform the GPUs of that day. Now, this need not hold true anymore with the latest generation of the Hopper GPUs from NVIDIA, as well as the H200 series, which is coming up. But this was true several years ago. And again, like the previous hardware, these are also available as Microsoft Azure IPU instances if you want to try it out. The other example is the Habana Gaudi chips. So there are like two generations of the Gaudi chips from Habana, which was later acquired by Intel for a fairly large amount of money. So the Gaudi V1 and V2 chips, when it came out, again, just like the Graph Core systems, they were demonstrating significant benefits over the then state-of-the-art Volta V100 GPUs from NVIDIA. The latest version of the Gaudi chip is Gaudi V2. One interesting fact about the Gaudi is that they have integrated high-performance communication fabrics available on the chip itself. So this is a very communication-rich fabric. If you want to try and access the Voyager supercomputing system at the San Diego Supercomputing Center, has these chips for you. So if you are part of the NSF ecosystem, then you will be able to get access to these solutions. The other, let's say, a bit more famous one is the Cerebras wafer scale engine. So recently, we all heard the news that the company is deploying a larger Cerebrus system. So typically your Cerebrus deployments were 1 or 2 nodes. They didn't go beyond that. But recently, Mr. Feldman, who's the CEO of Cerebrus, showed the deployment of a multi-node, multi-layer Cerebrus-based supercomputing system. So this is a very, very, very fat chip, close to 2.6 trillion or north of that 7 nm chips, and a 2D mesh fabric with over 100 petabytes per second of bandwidth. And again, this is available for folks who are part of the NSF ecosystem at the Pittsburgh Supercomputing Center. So all the solutions out there are available in one shape or form, either in an HPC system or an HPC cloud for you guys to try out. Now, the hardware is no good without an appropriate communication middleware to back it up. So we'll give a quick, let's say 10,000 or 50,000 feet overview of like parallel programming models. So we all grew up programming using shared memory based systems where multiple processes access the common shared memory. Later, the message passing interface, or MPI, was introduced to handle the distributed memory model, where the processes inherently knew that they were on distinct processing elements or nodes, and you had to exchange messages explicitly to perform to enable parallelism. Now, a middle ground between these two is what is called as a partitioned global address space, or PGAS kind of models, where the processes are exposed a logical view like a common, very, very large shared memory, but the programming model abstracts out the underlying distributed shared memory for the applications. So this is kind of a middle ground, and at a high level, these three encapsulates the kind of programming models available for you out there. Now, Nawras and Aamir previously mentioned that communication is very important, and especially the all-reduce primitive is critical if you are doing distributed data parallel deep learning training. Now, over the last 8 years, as the field of deep learning has evolved, we have seen several different requirements from deep learning frameworks as well as parallelism techniques from the communication systems. For distributed data parallel deep learning, all-reduce was the one and only primitive which was required for performing gradient aggregation. Now, from data parallelism, if you go to model parallelism, you will need point-to-point operations. And depending on the kind of model that you are doing, for instance, if you are using like a recommendation model, like DLRM from Facebook/Meta, you would be using all-to-all or all-gather kind of communication operations. You could also be using reduce scatter. If you are doing hybrid parallelism, it would be like point-to-point operations. So as the parallelism techniques have evolved over the last 8 years, the requirements from the communication library has also evolved. So this is where we have done a lot of significant work in the context of the MWAPICH MPI library, which has been around for more than 2 decades and is powering a lot of top supercomputing systems around the world. For more details, please visit our website. So one of the pioneering things that we did in our group about 12 years ago was the introduction of the concept of a CUDA-aware communication runtime. Now, what is CUDA awareness? So traditionally, what was the modus operandi for you to access data or move data from a GPU? So you would copy the data from the device to the host, move the data from host to host, then move it back from host to device. What if a communication library could do this? That is, can you pass a GPU buffer or a device buffer directly to a communication runtime through a communication operation like a send or a receive, and have the communication runtime orchestrate a high performance, low overhead data transfer over the website so that you get high performance and high productivity? So we were the first ones in the community to introduce this concept in ISE 2011 as a published work. And now if you look at it, there are a lot of GPU-aware communication runtimes from various other MPI vendors as well as hardware vendors. So if you look at NVIDIA, you have Nickel. If you look at AMD, you have Rickel. If you look at Habana, you have Hickel. Cerebrus has their own communication runtime. And this was a, let's say, a precursor or a pioneer in that field. And the upshot of all of this work is that you get near host-to-host communication performance in terms of latency, bandwidth, as well as bidirectional bandwidth if you want to move data from device on one node to any other device on either the same node or on a different node. So at a high level, this is the concept of a CUDA-aware communication runtime. And I also mentioned that there are other vendor-provided communication libraries. Again, unfortunately, due to lack of time, I'm not able to go into details of each individual communication runtime. Here, I'm using Nickel as like an example for all of them, because that was one of the first, let's say, vendor-provided CUDA-aware or device-aware communication runtime in the community. So Nickel stands for NVIDIA's Collective Communication Library. Initially, it was meant for one GPU, then a multi-GPU system, but still single node. And slowly, it has evolved with the requirements from the deep learning community. So let's say when the deep learning community only needed all reduce, reduce, and vcast, Nickel only had that. Then slowly, when it began to need point-to-point communications or more collective communications, Nickel slowly began to add support for all of these solutions. And right now, they also have support for internode communication in the Nickel 2. I think star series. I believe the latest version is 2.11 or 2.14, yeah, if I am correct. And a lot of other vendors like Habana, Gaudi, AMD have been using the same model as Nickel to develop their own communication runtimes for their specific hardware. Now, a quick high-level note. Nickel is great if you only want to perform deep learning, but if you want to perform generic scientific computing communication operations like MPI supports, the semantics of Nickel don't really match well with the semantics that is expected by scientific applications, especially on the point-to-point side. So Nickel is good, but with some caveats. So that is what I would say. Now, with this, let me hand over to Dr. Panda for the next section. But in the meantime, if you guys have any questions, I'm more than happy to take them.
Yeah, let me go ahead.
I have a question. So to do the, say if you're doing in-network or reduce, does it need to know the topology, and how would it know about the topology to do it efficiently?
So when you talk about in-network all reduce, are you referring to the features like Sharp from Mellanox?
Yeah, I'm not familiar with it, to be honest, but yeah, it's something like that.
So if so, yes, those kind of in-network reduction or communication technologies are very aware of the network topology. So when they set up the communication paths, they take the topology into account and make sure that the appropriate paths are taken with a view of the network topology. Does that help?
Yes, but how does it know? Like, let's say I'm just training a generic program. Mm-hmm. And the program itself, when I compile it, I assume that does it know? It wouldn't know the topology. So so is it the library that it calls to set up the all reduced tree? It somehow know about the topology?
Yes. So there are many ways in which you can identify the topology. So at a compile time, you obviously would not know the topology. I agree on that. But when you run the application, you would know what processes are involved and where those processes are located in the high-performance computing system. So once that information is available, there are several methods that you can do underneath to discover the network topology, discover the location of the individual processes, and create a communication tree or a communication graph, which is fine-tuned for that particular pattern.
I see. And so I assume this setup takes a while. So the advantage is that this is a one-time setup, so that it's okay.
No, this setup will not take that much time. It might take at most a few seconds to do the discovery. And this would have to happen for each job and for each communication pattern, because the allocation of the nodes that you get from one job to the other may be different. So it is a little hard for you to pre-compute what the pattern must be. But the creation and setup of the network topology aware paths will not take that much time. It would take a few seconds at most.
I see. So, but if I'm training the same distributed program, distributed model, that all reduced tree should look the same, no? For a while anyway.
Correct. So there is a couple of differences. The logical tree will look the same, but if my compute node changes, let's say if I have two switches. If in my first run I got 4 nodes in this switch versus 2 nodes in one and 2 nodes in the other. Now my logical communication pattern still remains the same, but my physical paths have changed. So that is what we need to take into account.
I see. Okay. Well, thank you. So it's somewhat dynamic.
Yes, it is very dynamic. So it has to be on a per job, per execution, per job size basis.
Thank you.
Hari, there is a question on chat from Cyan.
Sure. Let me take a look. So the question is, there is a major push in using mixed precision deep learning. Do these collective communication libraries support reduced precision accumulation? Thanks for the question, Cyan. That's a very good question. Yes, a lot of collective communication libraries do support reduced precision as well as mixed precision. Nickel has support for half precision. In the MPI world, we are also bringing in support for different kind of reductions in precision. So one is just using a smaller data type. The other angle that we in our group have been exploring over the last few years is the use of compression. So can you compress the data before you send it out, unbeknown to the application, then at the receiver side, decompress it and give it back to the application. So we have demonstrated significant benefits with this kind of an approach for traditional scientific applications like AWP ODC, which is an earthquake prediction application out of the San Diego Supercomputing Center. Also with deep learning applications like DLRM, deep speed, and things like that. So there are different ways in which one can achieve this. I hope that answers the question.
Yes, thank you. And can I quickly ask a sharp question since the point was brought up? So,
Yes.
so the collective schedules that you were alluding to, why can't currently, why doesn't it work for something like neighborhood collectives, where really you would have, you would benefit from that kind of a schedule, right? But still, the neighborhood collectives for most implementations fall back on P2P. As far as I can tell.
That is very correct. So the long story short is that the MPI implementers have not had the time to get to that. So like we in our group have been exploring Sharp in multiple ways. So we have introduced support. So if you look at Sharp, you only have support for broadcast, barrier, and all reduce. So using that, we have introduced support for reduce, scatter V, and all the non-blocking variants of it. The neighborhood variants are in our roadmap, but we'll get to that hopefully in the next few months or so. Thanks for raising that point.
Thanks, Hari.
Yeah.
Okay. So it's good. So let's continue. I think since we have a lot of materials to cover and
sorry, I have one last question.
Okay, sure.
On
Go
the
ahead.
Slack channel. Harry, you mentioned that you compared TPU with A100, H100. Do you have more details?
Unfortunately, no. We don't have details of the comparison right now. And I don't think anybody in the community has honestly performed an apples to apples comparison between even AMD and NVIDIA GPUs, let alone TPUs, the Habana Gaudis and the H100s. But the story on the grapevine is that the H100s still outperform most of the other compute devices out there in the market.
Well, H100 is a big muscle, right? It's yes. Like several times the scale out. So I'm wondering, when you compare which version of TPU did you use? And also what's the power consumption?
Those are very good points. We have not done any direct comparisons like that. And definitely not on the power consumption side, but the excellent points, Sasi.
And the other questions you mentioned, a GPU aware MPI, which is an excellent idea. So can you mention the data flow characters in that experiment? So it depends on the input, the backwards bypass, and the final output, the data ratio. So it's like if you have a small input and small output, and in the middle, you would have a huge of computing in the middle, it would make sense to some accelerator. But if you have a huge input output, but generally in the input, you would use GPU, right? So I'm wondering what's the traffic character did you use?
So in general, I have seen all sorts of things. I have seen the compute being very small. If you take the application, if you take the example of the Coombe application from Lawrence Livermore National Labs, so they are like very, very small kernels. Another example is the weather simulation application out of CSCS, I don't remember, Cosmo. So they also have like smallish kernels. But if you look at deep learning applications, the compute kernels are very large. The answer in short is it depends on the kind of application. So it is not to do with the middleware.
Exactly, it heavily depends on the algorithm.
Yes.
And the AI's algorithm is evolving. I would say it's changing every week. So that's why I'm wondering, when we mention the comparison, when we refer some performance, we need to mention what exact algorithm, what's the data traffic we're using. Thank you.
Sure. So just as a minor clarification, I was just talking about basic communication operations, not at an application level. Again, we have some other slides for that, which goes into much more detail of all the characteristics that Sissy was talking about, but that's probably for a different like avenue, not this avenue. But if you are interested, please send us an email and we'll be more than happy to talk about that further.
Okay, so with that, let's continue. So now, since we have understood like the deep learning frameworks, their characteristics, machine learning, and also HPC, now let's see how do we put them all together. Okay, so the broad challenge is to, if we want to exploit the HPC for machine learning, deep learning, data science framework, this is kind of like a problem statement. Like, how do we efficiently scale out? Of course, scale up is also important, but as most of the servers have like up to 8 or 16 GPUs, but here we are talking about like thousands of GPUs, so we have to scale out these frameworks and take advantage of heterogeneous HPC resources. So in the next few slides, through some animation, I'll try to explain these concepts. So if you take a look at this, like let's say all our deep learning frameworks, we talked about TensorFlow, PyTorch, you can have CNTK and all. Just like the traditional high performance computing applications, when you are running these on HPC systems, so they have some amount of memory requirements, computational requirement, communication overhead. Okay, so all these things we saw in the model propagation, forward, backward, gradient aggregation, etc. So from the first perspective, one has to really understand, and this is what is happening over the last several years. All these new frameworks, when they are coming, they are trying to integrate through, let's say, the MPI layer or through the nickel layer and all, and trying to optimize at that, the frameworks layer itself, okay, to understand the computation, understand the communication, whether they are scaling or not. And once you have that kind of a knowledge, then the question is, how do we design the communication runtimes? And this is where, like if you are going for a parallel and distributed training, one single node training is not sufficient. Even though you have, let's say, single node, you have multiple GPUs, the similar issues arise. Like how do we put them together? Like, for example, NVIDIA has the NVLink, AMD has the Infinity Fabric. So they're coming up with their own customized interconnects to make sure that those communication overheads are lower. And of course, like commodity networks like InfiniBand and Rocky and all those things go outside, okay? So in fact, in the afternoon tutorial, Hari and I will go over a lot of these kind of details. If you are interested, you are always welcome to attend that tutorial also. And the third thing is, here itself, in terms of the designing the runtime, I think there is a shift which has happened. I mean, we talked a lot about this all reduce and all. Those of you who are familiar with HPC, you will find that all reduce has been there. I mean, almost 20, 30 years. Many HPC applications depend on all reduce, but when you do all reduce in HPC applications, it could be 4 bytes, it could be 8 bytes, or maximum even 16 bytes. So all those algorithms which were designed earlier for all reduce were focusing on very small messages, whereas the modern all these deep learning workloads and all, when we are exchanging those kind of error propagation is coming, we are trying to do the all reduce. This message sizes could be very big. It could be several megabytes, and even the models are bigger, larger. You can even go to gigabytes. So there is a lot of R&D taking place about how do you implement these large message collectives. Okay. And we just discussed like this in that context, this CUDA awareness comes into picture. Hari mentioned about compression. So these are the kind of the new directions people are going to come up with solutions and then integrate them into the HPC systems so that the deep learning frameworks or machine learning frameworks can run fine in a much more scalable manner. And the final fourth one is co-design. And of course, this co-designing has been there. I mean, for many, many years. I mean, even for HPC application systems, people have been doing co-designing and similar kind of things we are seeing here, like depending on how these, like, let's say you are running on a real, let's say ChatGPT. ChatGPT is running with some, let's say, PyTorch or TensorFlow, and then that is running with an MPI or Nickel library, and that is going into the network, like with a DPU or SmartNIC. There is a lot of co-designing opportunities at all different various layers. You can optimize, and then in the end, you will see the complete system, hardware and software together, actually delivers you the best performance. So we'll keep an eye on these 4 different angles. So then what we'll do in the next section is to go over some of the solutions and case studies with respect to DL solutions, ML solutions, DAS solutions, and then we'll be able to map these into these 4 layers, so that will give you a very complete picture of where the state of the art lies, how people are working on the solutions, and then we'll go into some of the open issues, challenges, and hands-on exercises, and then we'll conclude. So if there are any quick questions, I can handle it. Otherwise, I think Nawras, you will take over here. Am I right? Nawras, are you there?
He might have stepped out. Can we take a 5 minutes break, Dr. Panda?
Okay. We can let's take a 5 minutes break. We are coming almost 1 o'clock. We can join like around 1 o'clock Eastern. 1 o'clock Eastern, 11 o'clock Pacific, right? No, 10 o'clock. I'm mixed up with my times here. 10 o'clock Pacific. Let's take a few minutes of break and then we'll start.
So while we are on break, Dr. Panda, then
yes,
I missed this thing about Dask, data science using Dask. So Dask is some framework, separate framework, or what is it?
Yes, Aamir can expand. So this is more into the data science. Aamir, go ahead.
Yeah, sure. So Dask is a framework, just like Spark. So, if you want to do some pre-processing of your data, filter your data, do some keyword searches. So Dask will facilitate for that.
Okay, got it. So it's again on parallel machines essentially for doing on big data such operations.
That's right, absolutely. So Dask is Python based. So it will go from your laptop to supercomputers. It will process the data on CPUs as well as GPUs. So yeah.
Yeah, and who introduced Dask? Who introduced first developed Dask framework?
So Dask is, it's a separate project, dask.org, but NVIDIA has also adopted this. They added support for, GPU processing of data in Dask. But Dask is an independent project.
Okay. Thank you.
Yeah. So there is a very active community behind it. They have a commercial spin-off as well.
So coming from the MPI world, isn't Dask a bit slow?
I mean, in what context? If you're
Maybe
about
starting things up, like starting up the processes, or maybe in communication itself, like if you use the RMA-like communication in Dask.
Yes. Yes,
Yeah.
so that's exactly what we address in our work, and we'll present briefly. So we have actually added support for MPI communication in Dask. So we replace, the TCP or the slow communication using MWPitch based communication, and I mean it already has support for UCX as well. So we will talk about some of those solutions.
Yeah. So Sayan, to answer the question, the Dask, if you know, these are the data scientists. So for them, like writing Python and things are much more easier. It's hard for them to write in the MPI. But then people like us who are designing the communication middleware, the challenge is how do we deliver the performance and scalability while they can do very easily programming. So we are trying to bring programmability and performance together. So we'll see that in the in this session towards the end, like Dask solutions. Okay.
Sorry, Dr. Panda.
No. We are fine. I think so. Nawras is back, I believe. So
Yes.
he can share, and then we'll get started. Yeah, Nawras.
Yeah, I'm sorry, I had an internet issue, but I'm
Okay.
Back. Yep. So okay, so we talked about distributed machine learning and deep learning on a high level. So now let's take a closer look at actual solutions and case studies. So a quick refresher of this slide, we have these different parallelization strategies. The data parallelism, we replicate the same model on different machines. Model parallelism, we split the model on different machines, and then hybrid is the combination of these two methods. Okay, so we'll look at some solutions for data parallelism first. This is the AmphapItch 2 high performance deep learning stack. And it's a software stack that enables efficient data parallel training on HPC systems. So at this higher level, we have the MLDL application. Then under it, we have the different DL frameworks like TensorFlow, PyTorch, MXNet. Then we have the distributed DNN training middleware. So like Horobot and Torch Distributed and DeepSpeed. So these software packages implement the distributed DL algorithm, basically. And finally, we have the MPI library, which orchestrates the communication on the HPC system. In this case, we have MPapItch 2 or MPapItch 2X for the CPU-based training, and then MPapItch 2 GDR for the GPU training. And this software stack is available on this website with a user guide on how to install and use. So MPapItch 2 and MPapItch 2 GDR libraries, they offer optimized communication collectives that are used in the distributed training, as Harry talked about. We've seen that like overhead use is very important. Other collectives are also important for different types of parallelism. So in this figure, we're looking at the overhead use latency for MPapItch 2 GDR. 2.3.7 compared to nickel. And we see that for the smaller message sizes, MPapItch 2 GDR is delivering better performance, so lower latency is better. For the larger message sizes, MPapItch 2 GDR is matching the nickel performance. So in deep learning, we mostly use large message sizes, but in some cases, we also use smaller message sizes. So basically, you can expect equal or better performance using MPapItch 2 GDR compared to nickel. So this is some scaling numbers on up to 1,500 V100 GPUs. So this is training the ResNet-50 model on the ImageNet dataset. So we have 1.2 million images. And scaling up to 1,500 GPUs, we get very good scaling. we spend 3 seconds per epoch. And then the overall training. So if you want to train the ResNet 50, we usually do it for 90 epochs. So we iterate over the entire data set 90 times, and this takes 4.5 minutes. So this is like a huge reduction and training time. Otherwise, it would take like days to train on a single GPU, and the scaling is nearly linear. And then this is on the CPU using the MFPitch 2x, the scaling on up to 2048 nodes. And like the convention is, okay, CPU is not good for DNN training, but this is not always the case, right? If you have strong CPUs with many cores on them, you can still perform DNN training very efficiently, especially if you have a lot of nodes. So this is the same exact benchmark ResNet 50 on the ImageNet data set, and the training time on 2000 CPUs is 7 minutes. All right, so now, is there a question in the chat? Okay. Now, data parallelism by itself cannot handle all the training scenarios. We observe 2 limitations here. If the model is too small, then
okay, so what you're saying is if I write on the container the date that I put it in your drawer, that's acceptable to you.
No, that is at least unique. It is not unique now. You can always claim that's more recent.
Okay. If you have any questions, please post them in the chat. Okay, so 2 limitations. If the model is too small, or if small to medium size, we might be underutilizing the GPU. Or if the model is too big, then the hardware won't support that model. So we won't be able to fit the model in the memory of the single GPU. So let's look at the first case. If the model is small to mid-size, we've noticed that for like models like ResNet 18, even ResNet 50, and the ShuffleNet and MobileNet, we are underutilizing powerful GPUs like the A100 when we are doing the training. So 43 to 63% utilization of the GPU. So our idea was like, okay, why don't we exploit data parallelism even further and place multiple instances of the DL model on the GPU? So like one GPU can host multiple models. And then we use MPI to perform communication on 3 levels. The first level is within the same GPU. So models need to sync up using onReduce within the same GPU. But then we have also communication between the GPUs. So that's like intra-node within the same node, but we have 2 GPUs that need to communicate. And then finally, the third level is between GPUs across different nodes. So in here we have like the 2 GPUs, and then each one is hosting 3 models, and then they are doing the data parallel training and MPI or reduce to sync up the weights and do the weight update. So by doing that, we observed from 30% to 62% on different DNN models. This is on the ResNet 18, and this is on the ShuffleNet, and this is on up to 16 nodes. Okay, so we talked about the first scenario. The model is small to mid-size. What if the model is too big and cannot fit in the memory of the single GPU? Then we cannot use data parallelism by itself. We'll need some sort of model parallelism. So let's explore the first type of model parallelism called layer level parallelism, and then we have subcategories under it. But in general, layer parallelism allows you to split the model on a layer basis when the model is too big, and the model can like reach large sizes due to 2 reasons. If we have like a lot of parameters in it, then obviously we need a lot of memory to store it, so it won't fit. But the second case is that if we have large images that we want to train. So this this figure here shows the memory requirement basically for different image sizes. So ImageNet is 224 by 224. We can train it easily on like Pascal GPUs, Volta GPUs, and then mesh tangling data. We cannot train it on like the Pascal GPU, which has 16 gigabytes of memory. But we also have like this extreme cases where we have very large images, like digital pathology. So we have 100K by 100K images. And like we cannot fit it in the memory of any GPU, even like the CPU, the host memory is not enough to fit these models. So under layer parallelism, we have the vanilla layer parallelism, which, as we said, we split the model. Let's say we have 6 layers. We have 3 GPUs maybe, so we split it into 3 partitions. First partition will have layers 1 and 2. Partition 2 will have 3, and then 4, 5, 6 are in partition 3. And then the idea is, okay, we're doing forward and backward pass, right? We can use point-to-point communication to propagate the activations in the forward pass and then the gradients in the backward pass. But keep in mind that we have this dependency graph, right? So we can only do one step at a time. So we can train the partition, do the forward pass for the partition 1 or 0 first, and then 1 and then 2. So if GPU do it, if the first GPU is doing work, then the other 2 GPUs are not doing any work. So we'll have at most 1 GPU active at any time. So we'll have a lot of idle resources. So this is one limitation of layer parallelism. We'll look at more advanced solutions later. For instance, pipeline parallelism improves on top of layer parallelism by basically pipelining many samples of data to be processed on these different GPU devices. So figure B here is showing basically the GPU utilization over time. So in here we're doing like forward pass on these different partitions. And then this is done on GPU 0, GPU 1, GPU 2, and so on. So we see this huge bubble in here where resources are idle, basically. Figure C shows pipeline parallelism, where we can queue many samples to be processed on these GPUs. So when GPU 0 finishes processing sample 1, or doing the forward pass for sample 1, it can queue up sample 2, and so on for the rest of the partitions. And then once all partitions complete the forward pass, you can start the backward pass. So we can still see this bubble in the middle. So performance is not fully optimized, but it's better than vanilla layer parallelism. So we see here some performance numbers of for AmoebaNet. If we do 2, 4, 8 GPUs, then 8 GPUs is 2.7x the speed up. So it's not very good scaling. And then under layer level parallelism, we have subgraph parallelism. Sometimes our deep learning model looks like this. So for instance, transformer models have this layer called multi-head attention. Transformer models are the basis for large language models like BERT and GPT and ChatGPT. So you'll find this architecture in them, where you have one layer that is feeding to many layers 2 to 9, and then all of these layers will feed to one layer 10. So if we use layer parallelism, we can split this into 3 partitions, right? Layer 1, and then these layers can be in one partition, and then layer 10 can be in one partition. But this is it will have workload imbalance, right? We're assigning a lot of things to one GPU. Maybe those layers will not even fit in that GPU. So this is how we do it with subgraph parallelism. We'll place layer 1 on GPU 1, and then layers 2 to 9, we'll spread them across the GPUs. And then we'll use point-to-point communication between layer 1 and all of these layers to propagate the activations, and similarly for layer 10. So you can see like there is a lot of communication involved in here. And also when GPU 1 is processing layer 1, the rest of the GPUs are sitting idle. So, similar thing for layer 10. So performance is questionable. We'll look at more advanced solutions and hybrid parallelism. But before moving to hybrid parallelism, we have one last type here under model parallelism called neuron level parallelism. And basically, for very, very large models, sometimes like we cannot fit the layer itself on the GPU. So we have model with many layers in it, and then the layer itself is too big to fit in the memory of a single GPU. So that's when we need neuron level parallelism, meaning we split the layer itself across multiple machines. So now we have like a layer with neurons in it. Neurons are placed on different machines, and then these neurons need to communicate between each other using like MPI. So again, performance will be not very good. So we have hybrid parallelism, which combines both data parallelism and model parallelism. So like we get the best of both worlds: data parallelism scaling and model parallelism solutions to this memory limitation thing. So first solution under hybrid parallelism, which basically combines both pipeline parallelism and data parallelism. So in pipeline parallelism, we said we can split the model right into partitions and then use point-to-point communication to propagate the activations and gradients. But we can also do data parallelism. So this model, which we partition into 3 parts, we can replicate it across different machines. So okay, this part is on one GPU, this on one GPU, this on one GPU. Maybe these GPUs are within the same node, and then on a different node we have another model replica that will also do the training. And then at the end of the training, meaning the forward and backward pass, we can perform an all reduce. So we're basically doing data parallelism. So yeah, in this scheme, we're using both point-to-point and collective communication. And by doing that, we see very good scaling. So the speed up is like on 100 and on 256 nodes. No, here on 128 nodes, right, is 110x compared to the one node. So very close to linear scaling. And so, okay, this design is called Hyperflow. And this figure basically shows if we change the number of partitions, we're gonna get different speed ups. So we optimize for the optimal number of partitions, and then we do the training to get this speed up. Okay, so under hybrid parallelism, we have other solutions. One of them is called data and subgraph parallelism. So you remember we talked about this. We said this architecture can be found in transformers. So one way to address this this issue is to basically combine data parallelism with the subgraph parallelism by distributing layer 1 across the different machines. Previously, we had it on one GPU. Now we're gonna spread it on 4 GPUs, and then we're gonna give each GPU different samples. So here, NS8 number of samples is 8 on each GPU. So we're doing data parallelism on these layers. And then for these layers, we are basically doing the forward and backward pass on them individually on each GPU. So they'll get the full batch, 32. And then for layer 10, it's similar to layer 1. We distribute the the samples across the different machines. So with that, we don't have any resources sitting idle. All the GPUs will be performing computation at any given time during the training. And with this design, training the transformer model on 1024 NVIDIA V100 GPUs gave 3.05x speed up over vanilla data parallelism. So even if the model fits on the one GPU, this is still better to distribute the workload like this, because you'll have more parallelism. Finally, we have the final solution that we're going to look at that combines both data and layer parallelism. So this is GEMS, GPU-enabled memory-aware model parallelism system. And it's similar to Hyperflow, but this is concerned with training very large images, right? So with Hyperflow, we train very large models, and in here we want to train on very large images. And if we look at this figure, this is showing the memory utilization over time, okay? And this is showing the forward pass and the backward pass. With the forward pass, memory utilization increases as we propagate through the partitions. And then in the backward pass, we start releasing this memory. And this pattern continues over the training. So we see this big bubble in here where we are basically underutilizing the GPU. So we have memory available. So what we do here is called bidirectional parallelism, where we can place another model in here so that another model replica, basically. So we can do data parallelism and utilize the resources that are sitting idle in here. So let's look at some results. So this challenge was motivated by digital pathology. So in digital pathology, we have these huge images of 100K by 100K pixels. They definitely cannot fit in the memory of a single GPU or even the host memory. And then there are two main problems with that. One of them is that, okay, maybe we can use like image segmentation, right? So if we have this large image, why don't we segment it to very small tiles and then perform the classification on each of these tiles? But that would be an issue because we're going to lose structural information. We'll lose context. So maybe these tiles are related in some way, but now we don't have any context. So we don't see the whole picture. So with the GEMS design, we were able to bring down the training time on this specific data set from 7.25 hours on one node to 27 minutes on 32 nodes. So 15x reduction in time. So this design basically enabled both large image training and achieved reasonable scaling. All right. So with that, I conclude the DL solutions. Let me know if you have any questions.
Yeah, so might be Nawras, if while people are thinking out some questions, since we'll be doing on hands-on, why don't you go to that page? Let's share some information so that people in the background can create accounts, those kind of claim accounts rather, not create accounts, and then we'll continue and reach there.
All right. So this is the slide for setting up the accounts for the hands-on exercises. Please open this web page. You'll find. Let me open it actually.
Yeah, just open up. Yeah. So this is we'll be doing the hands-on in there is a GPU cluster we have at the Ohio State University in our department. We have reserved it. So if you go to that, there is a page, just claim your account.
Okay, 1 second. So yeah, this is the web page, the Google Doc. Just sign in your name in here, and then you can use this username and password to log in to the system. So you just open a terminal and SSH with username, and this is the cluster address, and then your password is specified in the document, and then you can cd to this directory, and then once we start the hands-on exercise, we'll go from there.
Yeah, so there is a request on the chat. I'm just posting the document link there. Yeah, and the details are on the slide 130. Okay. Okay. So let people log on, set it up. So might be Aamir, you would like to continue?
Yes, I can. So let me just share my screen.
Yes.
Okay, so we'll now present some of the ML and Dask solutions. So the first solution that we would like to talk about is the CoML library. So this library comes from the NVIDIA Rapids project, and this aims to build an end-to-end data science analytic pipeline on GPUs. So as I've discussed earlier, so if you're trying to do machine learning today, the best library out there is scikit-learn, but it doesn't have support for GPUs. And then NVIDIA is trying to fix that issue by coming up with this CoML library. And so this is a GPU accelerated ML library, and it's fair to say this is the GPU counterpart of scikit-learn, and this supports execution of ML workloads on multi-node and multi-GPU systems. And as we have discussed earlier, other conventional libraries do not have support for GPUs. So here is the architecture level diagram of the CoML library. So if you look at the top figure here, we have Python-like interfaces. So this is scikit-like interfaces, and then we have algorithms implemented like popular algorithms like linear regression, logistic regression. But then CoML also has support for these math primitives, right? So let's say if your favorite machine learning algorithm is not available in CoML, you could still work at the primitives layer library and implement that. So if you look at the stacked version of the software, so from the top we have the Python ecosystem. It makes use of the Dask software, and then through Python, the core computational engine of CoML is written in CUDA, C, and C++ programming languages. So, we have CoML algorithms all implemented in CUDA because of obviously performance reasons. And then we have CoML primitives, and then obviously the CUDA library itself. And then, this is a complex piece of software. So Dask is capable of using UCX-based transport, but for collective communication, Nickel is also being used in the CoML software. So what we have done as part of this CoML work is that we have added support for MPI in the mix. So this is the same stacked layer of the software, but now we have added these yellow boxes here. So it's now basically possible to utilize MOPISH2 GDR, which is our GPU MPI library, and use that through MPI for Python wrappers in the CoML ecosystem. And we have some hands-on where you will use this part of CoML. So basically we'll run things in parallel, a simple k-means algorithm which will use MOPISH2 GDR to run things in parallel. So here are some of the performance numbers. So I'll just focus on the k-means result. So on the x-axis, we have the number of GPUs going from 1 to 32. On the y-axis, we have the training time. And, The training down time is scaling well with the adding, with the increase in the number of GPUs. But then we are also, let's say, on each data point, we have this yellow and red bar, and the yellow bar is the performance when nickel is used for communication, and the red bar is the performance when MOPS2 GDR is used for communication. And as you can see, we are basically seeing around 1.6x speedups compared to nickel on the 32 GPUs. And then, we also see similar trends for other machine learning algorithms. So with this now, I'll move to the Dask solution. So if you try and download Dask, the vanilla piece of software, obviously NVIDIA enhanced. So it has today 2 communication backends, TCP and UCX. And what we have done here is that we have added MPI communication backend to the Dask ecosystem, and we call that MPI for Dask. And in this, this is the stacked overview of the Dask ecosystem. Starting from the top, we have the Dask, libraries. Then we have some packages which are really handy, like Dask MPI, Dask CUDA, Dask Job Queue. And this distributed is the most important one here because this supports parallel and distributed execution like scheduler, worker, and client, but then it also has support for communication. So TCP is already available, UCX is added by NVIDIA folks, and then, these yellow boxes, MPF for Dask working on top of MOPS2 GDR through MPF for Pi is essentially our, additions to the Dask ecosystem. And obviously, if you're adding MPI-based communication, so, we need to make sure that, all these processes that we have discussed earlier, like schedulers, workers, and the clients, they need to be, started using the MPI ecosystem. And in that context, we rely on the Dask MPI project. So this is a library from Dask folks, and this helps, starting execution of Dask programs using MPI libraries. And then we, if we look at the implementation details, we rely on MPI-based communication. So we rely on, non-blocking MPI-based communications. But then these, non-blocking communications had to be wrapped around in Python, coroutines, communication coroutines. That makes things a little more complicated because, every time you're checking for the non-blocking communication to complete, we have to yield the CPU because otherwise we would, end up deadlocking, the Dask ecosystem. So, if you look at our papers, where we explain these pseudocodes, we talk at length about this. So here are some of the performance numbers. So this is on the Cambridge Wilkes 3 system. This is a fairly new system with A100 GPUs, HDR 200. It has 80 nodes. So on the left-hand side, we have, this is the QDF merge benchmark. And then, x-axis, we have 2 Dask workers, 4 Dask workers, up to 32 Dask workers, and each Dask worker is running on 1 A100 GPU. And if we compare the performance of our MPI solution with UCX or IP over IB, which is basically TCP, so we see that, we are 5x faster than UCX and almost 27x faster than TCP. We see similar trends for another benchmark, Matrix Dot, where we are, 5.2x and 9.6x faster than UCX and TCP respectively. And then we also see performance gains on, TAC Frontera CPU systems. The gains are not, just limited to GPU-based systems, but we also see benefits for, on CPU systems for having MPI-based communication backends. So with this, now I will hand this over to Dr. Panda for open issues and challenges.
Yeah, so I think, Aamir, there is a question from Cyan, sorry. Does MOPS2 GDR use the same ring all reduce strategy as nickel? Where is the improvement coming from? I can answer that. So Cyan, you saw, like, we showed some initial number, like how MOPS2 GDR compare with nickel. So small message, medium message, large message. So MPI has its own algorithms, and that's what we're using. And those algorithms for different message size, system sizes, but give better all reduce performance, other collective performance compared to nickel. And thus the benefits are coming from there.
I see. So basically what I'm trying to say is that, the existing algorithms which have accelerated scientific computation can also be used in the
Yes.
machine learning arena without actually changing much. Right?
That's correct. That's correct. So that's what exactly is our MPI design. So what we are seeing, we are actually in a broader range. We are going for a converged software stack. So the same MPI library, you can use it for HPC, machine learning, deep learning, Dask. Even in this tutorial, we'll not talk, but we also have a Spark MPI for Spark. So you just need like a one library, and all these workloads you will be able to run individually or even a mixed, because some complex workflows, they want to do some machine learning first, followed by HPC, followed by big data. So you don't have to use different kinds of stacks. So that is our longer term goals. And then we are making all these releases publicly available. People can download and get the best performance for their workloads. Okay. So if there are no other questions, let me continue, and then we'll come back and then trying to do some of the hands-on exercises. Let me open up, and I think there is another question from Albert. I have heard that for the training large models, there might be salient data corruption inside processors, which affects the training of the model. Have you guys been seeing that, and how do you handle that? Do you train the model multiple times? I don't think we have seen that. Right? Aamir or Nawras? Data corruption?
Yeah, I've heard that might be not just data corruption, but even the compute, because a lot of the places are not, don't have ECC check, or, during the computation, bit might got flipped because of, alpha particles or whatnot, and it's not detected. So just wondering.
No, I mean, at least we have not focused. It might be there on some machines or some high altitude, those kind of things, but we ourselves have not focused on those angles.
I see. If you don't mind, I ask another question. So
sure.
So then is there undeterministic in this training process? Because there might be some race condition on which data set got through first. So the back, would that cause the back annotation, the back propagation changes the parameters differently? So is this whole process deterministic or non-deterministic?
Yeah, might be. Nawras, would you like to answer that? Yeah.
So like what process are you referring to exactly? The training, like forward and backward path?
Yeah, especially when you're doing different parallelism.
Yes.
Would that cause some sort of indeterministic behavior?
So yeah, I mean, so also that depends. So with deep learning, the DNN models, the weights of these models are randomly initialized. So you have a random factor. Also, the way that you feed the data to your model, we're using stochastic gradient descent, which means we're randomly sampling data. So there is like this factor of randomness, but you can also fix your random seeds. So if you want to reproduce these experiments, you can always fix these random seeds so you can reproduce exactly the same results. So if you train the same model on the same data with the same random seeds, then you should expect exactly the same conversions, the same weights at the end of the training.
Okay, so you don't think there are any sort of race conditions during the parallelism that cause indeterministic behavior?
No, not in communication.
Okay.
No.
Thank you.
Sure.
Okay. So let's continue. We saw a lot of solutions. So let's take a look at like what are the kind of the open issues and challenges in this field. This is just like if you are a student or you are looking for problems, or trying to take a look at what things are coming. So broadly, I mean, these are some of the things. Again, this field is very vibrant, as you know, a lot of things are happening. These are like the 5 different angles we'd like to focus on. First of all is the convergence, and then the scalability, then benchmarking, standardization, open exchange, making AI accessible, and then also similar kind of things for the data science domains. So along the first line, of course, in the last few years, especially, there is a lot of convergence taking place between ML, DL, data science, and HPC. In fact, any new clusters being deployed these days, you know, they are saying it is an HPC and AI machine. It is no longer like just an HPC machine. And we saw this distributed model DNN training, that is the biggest problem. Inferencing traditionally has not been an HPC problem, but now they are coming up. Okay, just think of like ChatGPT. I mean, at any given time, I mean, millions of requests are coming to the servers where the ChatGPT is running. So how do you solve those things? I mean, if you do sequential manner, then it may not be good, but it is a kind of a high throughput problems, high throughput computing problem. So a lot of requests are coming. How do you handle those? And people are coming with better and better parallel solutions there. So, and obviously HPC, as we saw in terms of interconnects, programming models, they are trying to extend help to run all these things in the best possible manner. So in that context, some of the needs of the ML, DL, and data science frameworks are an exact match, because these were the computer intensive problem. If you have been in the HPC field for 20-25 years back, you remember like people used to define grand challenge problems. Okay, so now these AI workloads are actually large grand challenge problems. Okay, but of course we talked about, I mean, to design this communication runtime, especially you need to focus on large message communication, the CUDA-aware communication, the collectives. We talked some of those things. So then the other thing, then what happens on the HPC systems, this batch size makes a big impact. We talked about that batch size, especially if you use large batch size, it will try to reduce the amount of communication and competition before you synchronize. But then there is a limit to the large batch size. So this is also becoming very active research. People are working on all different architectures, how best to exploit this overlap and latency hiding techniques. I think we had one question like in a real machine, like what is the CPU is doing versus let's say what the smart NIC will be doing in future, where the competition is happening, who is doing IO. So a lot of work is taking place in this context. So then gradually what we are seeing is the DNN sizes are increasing. Okay, really like large model here, if you see this is the pointer, it has 137 billion parameters. Okay, so of course the training is very important here, but then what happens many times, the data sets are also becoming very large and the models also becoming large. So you cannot fit it into a single GPU. Okay, so then this is leading to a new research direction called out of core training. Okay, many of you, the old timers might be knowing like in the history, like a HPC, it used to be like out of core sorting. How do you do if your entire data set, you cannot fit it in the memory, physical memory, how do you do the sorting? The similar ideas are, or challenges are coming here and people are trying to provide solutions. So then as we are heading into these directions, people have started also talking about like, is there a standardized interface? Just like think of message passing interface was not there, like let's say 40 years back. Every vendor had their own library, but then gradually it came to standardized. So that field is now everybody designs based on the standard, but something like for the deep learning, it has not come yet. For example, will there be a deep learning interface or DLI, or where it will come from, like HPC side or DL side? Can there be a collaboration across communities? Then if we do that, then what about benchmarks? This direction is moving faster. There are some references here, and especially I think the ML perf. Some of you must be familiar, and if not, you can get into more details. I think they are trying to standardize so that you can actually compare performance of your training, inferencing for different models across different hardware in a very standardized manner, and then we'll see how that momentum continues. And then especially in the field of AI, you know, there is a lot of discussion taking place, make it accessible, make it democratized, open exchange. So, and that's how this open AI started and the ChatGPT has come. And then there is also another thing is taking place, which is called Onyx format. So this is an open format to exchange trained models. So for example, if you had trained a model like let's say 6 months back, and in some context might be using a TensorFlow, now you want to use PyTorch, and then keep on enhancing that model. So how do you continue instead of starting from level 0? So this is where like a lot of actions are taking place. You can actually convert back and forth across different models on different systems. So similar things, the data science, I think we had some discussion earlier, like a data science, all these tasks and all are coming from the data scientist perspective. Programmability is very important for them. But then the question is, how do you get the performance also? And this is where like NVIDIA is putting this Rapids accelerator for Apache Spark. So they're actually currently adding support for GPU processing. So you can find out more details. In our group, actually, we are trying to utilize now all those CUDA-aware MPI, maps to GDR to in fact accelerate on the GPU-based systems. Also, in that context, you will see even API communication layer can also extend help in the data science. Okay. So here what we'll do is we have 15 more minutes. Let me go and conclude the tutorial in an official manner. So if you have some questions or if you have some constraints, you can drop off, and then those who are interested in the hands-on can stay there and will be there for you for some time. Okay. So let me move ahead and finish this to the conclusion. So basically what you saw in this tutorial, it was very short, like a 3-hour tutorial. And by the way, who will give this tutorial at Supercomputing? It is a day-long tutorial. It has been accepted. So we'll really go into a lot of details. If you're at SC and would like to learn more, please feel free to join us at the SC. But otherwise, you will see there is an exponential growth in the machine learning, deep learning, data science. So what we did in this short time frame, we provided an overview of the issues, the challenges, and the opportunities for designing efficient communication runtimes, and then demonstrated the performance benefits at the upper layer. And we'll have a set of hands-on exercises, so you can actually get a feel that how this field is working, and so that you can actually utilize a lot of these tools for your own research. Okay, but broadly, if you see, it is not just like these days. It's like it is no longer like isolated to some silos. I mean, people have been working across the stack. Like we had some questions starting from instruction sets to the math library to the middleware to the frameworks kind of things. So, and that is the picture we want to see as we move along. So last but not the least, I'd like to thank all our sponsors. What we are trying to bring here is actually a work from almost like last 22 years. The MPI library that work has been going on in my group for last 22 years. So a lot of students, staff, they have contributed to this project. So I'd like to, these are all my heroes. So I'd like to really salute them in this presentation. So here are our pointers, email addresses. If you have any questions, please feel free to ask us. And as I said in one of the HPC section, we'll be giving Professor Harish Subramoni and I'll also be giving a tutorial in another 2 hours. That is mostly focusing on the networking aspect, high performance networking, what are the challenges, and how the modern networks interconnects all are taking shape, what are the performance numbers there. So if you are interested, you can also join us in that tutorial. So with this, I think let's get back to Nawras. If you can get started on the hands-on, those of you, please stay. Or even if you don't want to do hands-on, you can still listen to see how how this framework can actually run on the CPU, GPU clusters. Thank you. Nawras, are you there?
Yes, I am here. I'll share my screen.
Yes.
Okay. So is everyone able to log into the RI2 system?
How
anyone-
many of you, since we'll be doing the hands-on exercises here, it'll be good to get some feedback. Otherwise, we'll be just talking in a vacuum. Okay. So please unmute yourself if you can ask questions so that we will exactly know, is it working or not working? What problems are you facing? Okay. Go ahead. Yeah. So we got a response.
Yeah, thank you, Giovanni.
Giovanni has logged. Yeah.
Anyone is having an issue with the login? If so, please unmute or post it in the chat. Okay, but I'm assuming everyone is with me. So the first thing we're gonna do is cd to this directory here. Cd to opt tutorials dl tutorials labs. Okay, so we are here. We have labs 0 to 4. And then we're gonna look at this README file. Open. Okay. So in this README, we have the commands for all the labs that we're gonna run today. So you can just copy and paste them. If you copy and paste from the PDF, you might see some issues because you'll copy like faulty characters. So please use the README. So I have it open here. And then we're gonna go to lab 1. Okay. So an overview of the labs. Lab 1 is DNN training using PyTorch. We're gonna do it on a single GPU and multi-GPU. And then lab 2 is with TensorFlow, also with single and multi-GPU. Then lab 3, we're gonna look at ML models using QML, K-means on the single and multiple GPUs. And finally, lab 4 is data science applications using Dask, the setup and one application. So, okay, we're gonna start with the first lab. And the objective of this lab is see how to train a PyTorch model on a single NVIDIA GPU first. Then how we can perform distributed training using InfiniBand and NVIDIA GPUs. And we will be using the EmphaPitch library. So in here, we are going to use a benchmark provided by Horvad. We talked about Horvad, which is the middleware that implements the distributed data parallel training algorithm, which sits on top of EmphaPitch. And we're gonna run the ResNet 50 model with synthetic data. So there is no data loading. We're interested in measuring the throughput for now. So we're not gonna look at the accuracy, we're only gonna look at the throughput. And then we're gonna write it with batch size 32 for 10 iterations. Thank you, Giovanni, for posting the command. We're gonna run it here and see what we get. So this is running this benchmark that we talked about on one GPU only. We're gonna run it for 5 iterations and see that kind of performance we get. Okay, so again, ResNet 50, batch size is 64, number of GPUs is 1, and this is for 5 iterations. So we're gonna take the average of these 5 iterations and then see the images per second on the one GPU. So this is the throughput. How many images can we process, do the forward and backward pass on? And it's 334 images. Now next, we're gonna run the same benchmark, but on 2 GPUs with EmphaPitch 2. So this is EmphaPitch 2, not EmphaPitch 2 GDR. This is not the GPU aware library. We're gonna compare both of these and see which one performs better. Okay, so in here, we see that if we run on 2 GPUs, we get 439 images per second. So like the scaling is not very good because we're not using the GPU aware library. This would do very well on a CPU. But if we want to run on the GPU, then we need to use the MPI library that is GPU aware. So let's run this command next. So you can see the command is different here. We're using this MV2 GDR, MPI run. We're saying use 2 processes and use these 2 nodes, GPU2 and GPU3, with these parameters that will optimize the performance, and then just run the same benchmark with the same batch size, same number of iterations. So in here, we see that the performance is 630 compared to the 334 on the 1 GPU. So very good scaling, almost 1.9x. And we expect to see the same scaling if we do 4, 8 GPUs and so on. Okay, so this is PyTorch. Let's look at TensorFlow. So we're gonna CD to this. I'm gonna post it in the chat. And then we're gonna run this command, which is training TensorFlow on a single GPU. Again, same benchmark, ResNet 50 for 5 iterations. So TensorFlow has a small overhead to do the setup, so we might see a slightly longer time. Let's give it a minute. So it's basically like loading different libraries like CUDA and cuDNN, which implement different deep learning kernels to accelerate the performance. This is also done in PyTorch, but this is shown explicitly with TensorFlow. Okay, so with TensorFlow, we see 338 images per second on the 1 GPU. Now let me post the second command. So now we're gonna do it on 2 GPUs. Okay, and then we get the performance numbers. And we can see 625 images per second, which is also like almost the double the performance. So Giovanni, you're saying, okay, you're saying the performance has not improved much. Is that normal? It did not improve from where to where?
For the initial runs, like before this latest one, they were not,
yes,
but like the first 2 was just like a bit of improvement.
So for
the
you mean for the PyTorch experiments?
It was like 334 or like 329. So I was like, what's going on? But the latest one goes down to like about 312.
Oh, yeah. So these are showing per GPU, right? So these 0, 1, 2, 3, 4 are showing per GPU, but then we have two GPUs that are training at the same time. So in here, we're gonna look at the summation of both GPUs. So you should look at this last number and it will tell you the overall performance.
That's what a clarification now.
Okay. So with that, Aamir, are you here?
Yes, I am. Yes.
Okay. Do you want to share your screen? And
Yes.
okay.
So you're seeing Nawras, right? On the
Yes.
right hand side of the slide.
Yes.
Okay. So next up we have the QML lab. And in this, what we are going to do is, I mean, these are pretty simple. So first we are going to do k-means on a single GPU, and then we are going to do k-means on multiple GPUs. So I'll just go here. So this is the first task, and I have the README open. I actually don't have it open, so I'll just open it. I'll go down to section 3, lab 3, and here basically this is the command, and I'll just copy this. And what this command is doing is that, you know, I'm asking for one node, and each node here is one GPU, and run this QML k-means single, you know, training algorithm. So I'll just go run it here. And this is now going to run. And basically what we are going to do, the value of k, I mean, this is our input data. So it has around 250,000 rows, 298 columns. And, you know, this is all coming from data.txt. This is running on a single GPU. And we are basically going to run this for 3,000 iterations. And towards the end, you know, the time will be printed. And in the next experiment, so basically we ran it, and it basically, if you look at the time here at the bottom, it says that, you know, it took around 28, you know, seconds. So what we are going to do now is we are going to run this now on 2 GPUs. So using this other command, and I'll just copy this, and this is now going to run. So, and what we are going to expect here is that, you know, the overall execution time would remain the same, but now we are running twice the number of iterations, right? So which basically means that, you know, we are almost, if the time stays the same, and we are, you know, doubling the number of iterations, then, you know, it means that, you know, we are running at almost twice the speed up. So in this particular case, you can see, you know, from 28 seconds, the time has gone up to 29. So we expect this to be around 1.9x, you know, speed up on two GPUs. So with this, I'll move to, you know, the next Dask section. And in this Dask section, what we are going to do is we are going to basically declare a CuPy array. So CuPy is the GPU version of NumPy. So we'll just declare a NumPy or a CuPy array. CuPy array basically is stored on the GPU, and then we are going to take a transpose of this array and then take a sum of the corresponding elements. That's basically our benchmark. And what I mean, the first thing that we are going to do here is the setup. So I'll just go do the setup. I mean, you can just copy paste the commands. So I'm making a directory. So I'll just copy this mkdir command. I mean, you will also see this on the right hand side, and then I'm copying some of the files to this new directory that I made. And I'm doing this because I'm going to so now basically I have, you know, if I go here, go in this new directory and do an ls. So this is lab 4. So I basically see all these, files. So Coupa_bench and run Coupa_bench are the two relevant scripts. Okay.
I believe, correct me if I'm wrong with time change, but I believe the next tutorial is supposed to start around now. So if you're at a point that
Okay.
you could wrap up soon, that would be great.
Yeah, we are almost done. Yeah.
Okay, thank
We're
you.
almost done. Yep, sure. So I'm, so in this case, what's basically happening is that we'll, first run this using TCP device. So the time comes out to be around 12 seconds. And then if we run the same thing by just, modifying one line of code from TCP to MPI, the execution time decreases by 3 or 4x. So in this particular case, it comes down to 4 seconds. So, and this is just a single, line of change. And so the reservation is going to be there for the next hour or so. So, I would invite all of you to kindly, go through this tutorial. And if you have any questions, please send them to us. Thank you. Over to you, Dr.
Yeah, and Amanda, we had actually finished the tutorial officially earlier, okay? Then took the hands-on. So this concludes officially the tutorial. I hope all of you liked it. Again, those if you are interested, please continue with the tutorial, the follow-up ones, and Professor Harish Subramoni and I'll all be back again at 1 o'clock for the other tutorial, which is high-performance networking technologies. Thank you.
Perfect. Thank you very much.